Good evening, y'all, and welcome back to another Sunday night Electronics Bash live stream, where we get together on Sunday nights and talk about anything that isn't washing our hands, and by anything I mean electronics. This is the 5th week in a row that we're doing our series on taking you from knowing nothing at all about Arduino, right, pulling that dusty Arduino kit out of your closet that you've been meaning to work on for weeks and weeks, or years and years in some of the cases that I've heard about, and taking us through the fundamentals of working with Arduino and how it can be used to do all kinds of awesome things. I think we're going to have a really good time tonight. As always, we're going to give the stragglers to the stream just a couple minutes to catch up before we dive right into our topic for tonight, which will be talking about transistors and FETs. And if you don't know what either of those things are, that's fine. That's what we're going to talk about tonight. I think last week I said we were going to talk about relays as well, but as usual, as I started to put together the content for this week, there's just so much to talk about, and I'd rather slim down the number of topics and give ourselves some breathing room, and then be able to go deeper into detail about some of the things that we want to talk about. I realize I haven't gotten the chat up where I can see it. Hello, couple familiar faces in the chat tonight. How's it going, y'all? I hope you've all had a good chill week since we saw each other last week. I hope you're all enjoying a relaxing Sunday evening and drinking something if it's your choice to drink. If it's not your choice to drink, that's fine. But as you might be able to hear, I am having a refreshing Alley Time Pale Ale from our friends at Spiteful Brewery right here in Chicago. A delicious local brewery just around the corner from me. Kenneth Finnegan, as always, will be our moderator for tonight. Chris is back. Hi, Chris. How are you doing? Chris, I think I saw a rumor on social media somewhere you were looking for some Arduino projects to keep you busy. Possibly some lighting-related projects? Interesting. I think maybe tonight's stream may have some material for you, and if it doesn't, well, that's on me. And I think we should find something to keep you occupied. Chris is a props master at one of the universities here in town, and the number of shenanigans that I worry that Chris might be able to get up to with the bevy of skills and tools and resins and materials at his disposal is a little troublesome. So we should all do whatever we can to keep him busy. Just starting a lighting project. Yes, tell us about your lighting project. What are you working on this week? And if you have a tasty beverage of your own out there, something that's keeping you refreshed tonight, I wanna hear about it. What are you drinking? Mine is a pale ale. Let's see what we can learn about this. No facts, just a pale ale with a little angry face. Sort of the opposite of how I'm feeling. Oh, that's right. We tweeted about your lighting project. Yes, that's super fun. Yes, I wanna see pictures of that lighting project when it's coming together. Christina Finnegan's here tonight. Hi, Christina. How are you doing tonight? Very good to see you. Lee Fisness, hello. Good to see you. Having an Oberon, also in Chicago. Kenneth, that is not the correct verb for using Twitter. I am absolutely sure. Yeah. Brian's back tonight. Good to see you, Brian, as well. Awesome. What a good selection of humans. This will be a lot of fun. PF Janky, Palmer's back tonight. Changed a light bulb this week. That's a lighting project. That counts. It's maybe a little bit higher voltage than what we're going to talk about this evening, but that's an awesome project. Travis is also here. What a good group of people. If there's anyone who doesn't, hasn't shouted out tonight, I'd love to know just, who's out there, where you are, what you're sipping. I hope you're all doing well out there. I care about all of you, and it's nice to come together on these Sunday nights and just like nerd out and learn some things, and I'm really stoked about it. But with that said, I see our countdown is up, so let's get into it, y'all. We got a lot to talk about tonight, and we have a lot to talk about, but only a couple of core subjects. So as always, I hope you will ask questions, put them in the chat, and we'll try to answer them as best as we can. It's also, I know, I was talking to a couple people who specifically were like, I'm excited to learn about FETs tonight. I've heard so much about MOSFETs. I think the bulk of our time tonight is going to be, we're going to start with transistors just because I feel like they're a slightly easier concept to understand, but almost everything that we learn about transistors and how we use them in circuits is directly applicable to how we use FETs. And so we're going to start with transistors as our base of knowledge and then move into talking about FETs after that, because we'll sort of build in that way. So if you're here looking for FET knowledge, it's coming, and all of what we're going to talk about to begin with is applicable. Just know that we're going to sort of start from our base level of transistors and work our way up. Awesome? Cool. Well, let's dive right into it. Talking about transistors and FETs. Or a FET, I should say, FET is short for field effect transistor. So really, we're talking about transistors and transistors, but we'll get into the terminology in just a second. So We're going to talk about two types of transistors: bipolar junction transistors, or what I casually just refer to them as transistors, or BJTs. You'll see them abbreviated, bipolar junction transistors, and field effect transistors, or FETs. And we're also going to sort of apply that knowledge at the end of the night to continuing our look at 7-segment displays. So at the end of the stream last week, we wired up a single-digit 7-segment display. Let's see if I think I still have it floating around here. I realized I'm running out of breadboard, so I had to unwire my demo from last week to be able to do it. So you see, I now have a 4-digit 7-segment display wired up, and that's what we're going to get to by the end of the night tonight, is driving not just a single-digit, but a multi-digit display. So just a little teaser of where we're going to get to with our transistor knowledge there. So why do we want to talk about transistors and FETs? Well, as we sort of hit on back what feels like a million years ago, 4 weeks ago, in our very first Fundamentals of Arduino stream, there are some limits as to the voltage and current that your Arduino can supply. At an absolute maximum, 40 milliamps per pin is what the little chip, the ATmega that's on the Arduino, can provide, or ATmega, sorry, kind of. We like to keep it below about 20 milliamps a pin just for safety, and regardless, about 200 milliamps max, either in or out of the Arduino, is all you can supply. You can only, in terms of voltage, you can only supply, say, an input voltage that's half a volt below ground or half a volt above your supply voltage. So in our case, minus 0.5 or plus 5.5 volts. And that, as we've seen, we spent 4 weeks just using those capabilities to do very interesting things. But there's lots of things in this world that run on voltages above 5 volts, and there's lots of things in this world that need more than 20 milliamps to run. So how are we going to power them? If you're guessing that we're going to use transistors and or FETs, then you have a good sense of pattern recognition. That's exactly what we're going to do. And the way we're going to think about them is something like this. If you're thinking about how might I use an Arduino to control something higher powered, well, the circuit on the left here, this circuit over, oh, you know what I didn't do was reset up my mouse settings again. Wow, that's exciting. You guys get to look at the side of my face while I once again restore my mouse settings so you can see what the mouse is doing. Oops. That's all right. Let's see here. I'm going to set up my pointer so that you can see it. For some reason, it likes to unapply my settings about once a week, maybe during a Windows update. I don't know. It still thinks it's still applied. This is clearly the quality content you guys come to this channel for, I'm sure. All right, let's get you back over to the computer. We'll get back into the slides. There we go. So now you can see the little yellow dot that is my mouse. Whew. We'll cut that out in post. It'll be fine. Nobody will see that. So on the left here is the Arduino driving an LED circuit that we've used every week from the very beginning, right? We have a digital pin, we have a resistor, we have an LED and ground, right? The digital pin is providing a little bit of current, or I should say 5 volts. It's being limited in its current by this resistor. The current is flowing through the LED and turning it on. But let's say that this LED, or some other kind of load, needed more than 20 milliamps to turn it on. What kind of circuit could we think up that would allow that much current to flow? Well, this circuit on the right here is one way that we might think about this, right? If we had, a higher current load in this LED here, what if we, instead of using the digital pin to directly control the current flowing into the LED, what if we just use it to control some kind of switching device, something that we could just open and close, and then we could source our power not from the digital pin, but from some other higher current power supply, right? So we'll use just our little bit of current or voltage that's available to us to turn this switch on and off, and then we'll get that voltage supply that's a sort of a higher current limit from somewhere else. And this is exactly what we're going to be doing tonight with first transistors and then our field effect transistors. So let's start with our first family of transistors, our bipolar junction transistors. You may have seen them floating around in the world. You may have not. They come in many, many different shapes and sizes. In fact, I think I have a little pile of them here. Here, let me move this demo out of the way. I just reached into my bin of bipolar transistors and pulled out some assorted examples. They range from the very small. In fact, in the realm of transistors, this is not very small. This is actually a pretty beefy size. This one is an MJE 9712. I don't know what that one is. Just a scrap transistor, right? We get a little bit beefier with something like this. Sometimes you see them in metal cans like this. And as you might expect, the larger the transistor, the more power they can handle, right? So this one has a case that's partly plastic, partly metal. Something like this in a big fat metal case is probably because it's meant to get really hot or handle a lot of power. They also go much smaller in size from here, right? These are all through-hole components. You're meant to solder them onto a circuit board or stick them in a breadboard. You might see, let's see if there's any on here. They go down in size also to things like a surface mount device, like you might see on your Arduino Uno how there's actually no holes through the circuit board there. The device is just soldered onto the top. There are transistors in that form factor too, and in fact they get very, very, very small. And I think I might be wrong. This little tiny 3-terminal device here, I think is a transistor that's related to whether this Arduino runs off of battery power or the USB power or the barrel jack power here. So I think that little tiny guy is a small little low power transistor. So just to give you a sense of scale, these things range from the very small to the very large. But they all have some things in common. They all have 3 terminals, 3 points of connection. And they might look very different depending on what kind of device you're talking about, right? For stuff like these little 3-hole guys we were just looking at, I have 1, 2, 3 pins right there. So those are my 3 terminals. For some of the bigger metal ones, the metal case itself is actually one of the points of connection. You're meant to attach these 2 pins, these 2 wires here, to points of your circuit. And then this whole metal case gets attached to usually the metal chassis of your device, and that forms one of the points of connection. So things may look different depending on the size of your transistor. You know, for a little tiny surface mount device like we were looking at on the Arduino there, you might have 3 little tiny tabs coming out the size, but 3 tabs all the time for your BJTs, your bipolar junction transistors. And they have names. Your 3 terminals are collector, base, and emitter. And we'll get to what those mean in just a second here. But I want to say this early, and I want to say this often. When you're working with a transistor, you want to be extra super duper triple dipple sure that you know which of those points of connection is which for the specific transistor you're looking at, because there is no standard in most cases for which connection, which pin on which side is which terminal. For example, a lot of the kits that are out there, if you're starting with, you're getting started with Arduino kit, will have one of these 2N2222 transistors. It's a very common medium power transistor. It comes in a little small case. In fact, I might have some here. Let's see. If not, I have something very close to it. Let's see. I have a box of transistors. Let's see. 2N5904, BS170. Let's see. So these are the same size. I'll just use these for illustration. So you may have a few of these in your kit, I suspect. Little tiny package right there. So for the 2N2222 specifically, if you're looking at it on your data sheet, if you've Googled 2N2222 data sheet, it will tell you that the pins are in order, if you're looking at the face of it with the labeling from left to right, are emitter, base, collector. But when I went to pull one out of a bin tonight, I discovered that I had a P2N2222. Sounds very similar, but it turns out that my P2N2222 actually has the connections in the opposite order. You see up here I've got collector 1, base 2, emitter 3. So I'm actually going collector, base, emitter, not emitter, base, collector. All this just to say, be extra careful that you know for your exact transistor model what order your connections are in, so you're not connecting things backwards or upside down, because they, in the best case, don't work very well, and in the worst case, blow up. So you've been sufficiently warned. There are 2 flavors, 2 species, 2 internal workings of bipolar junction transistors, and we're going to get into how both of them work, but I want to introduce you to the symbols that we use for them in circuit diagrams right off the bat, so that when we're looking at them, you know what you're looking at. These are the 2 symbols for the 2 types of bipolar transistors. They're called NPN and PNP transistors. And it has to do with, the naming comes from, there are basically essentially 3 pieces of doped silicon that has some materials added into it to either make there be excess electrons or deficient electrons. They are called N-type and P-type materials. In the NPN transistor, you have 2 layers of N with a P sandwiched in the middle. In a PNP transistor, you have 2 layers of P with an N sandwiched in the middle. NPN. PNP. They're not actually sandwiched in the middle. The construction is somewhat more complicated than that. But for the essential working of a transistor, you have, a sandwich of P in the middle of 2 N's, or the sandwich of N's in the middle of 2 P's. That will affect how the transistors work, which we'll get into in just a second. The mnemonic that I like to use for remembering which of these symbols, because these symbols look very similar to each other, remembering which one is which is, I use the following mnemonic. Both of them have this little arrow that I'll explain in a second here. I have this little arrow pointing outward in this case for the NPN transistor, and for the PNP transistor, I have this little arrow pointing inward here, and that forms the base of the mnemonic. For an NPN transistor, let me get that menu to go away. Go away, menu. Go away. For an NPN transistor, you'll see down there, the arrow is not pointing in. The in forms the last N. And for a PNP transistor, the arrow is pointing in proudly, right? NPN not pointing in, PNP pointing in proudly, right? So if you're looking at a circuit diagram that you've pulled from the internet or from these slides somewhere, and you're seeing a transistor and you're not quite sure what kind it is, you can use that mnemonic to help you tell which type is which. I should say, because I don't think I mentioned it at the beginning of the stream, if you want to follow along with these slides or with any of the circuit diagrams that we'll be using for tonight, you can find them in the link below just here at my website, jeff.glass/electronicsbash. That has links to all of the slides from all the streams that we do. It has circuit diagrams. It has all the code that we'll be using, or at least any of the code that I thought to write before the stream started. Usually we write some code in the middle of it as well. But yeah, go to jeff.glass/electronicsbash and you can see all this code and follow along with these slides in real time. You don't have to memorize all this as we go. Cool? So, two flavors of transistors, NPN, PNP. And I said I would explain what this little arrow in this symbol is. That little arrow represents a diode inside the transistors. We talked last week about light-emitting diodes. You remember we talked about we have, this two-terminal device that has a positive and a negative side, an anode and a cathode. You have to apply your positive voltage to your positive side and your negative voltage to your negative side, your cathode side, and current will flow across it, and you lose some voltage to your circuit, right? We had this idea of a forward voltage that came into play when we were lighting up LEDs that changed based on the color of light that was being emitted. Hopefully this all rings a bell. If it doesn't, you can go back and watch last week's video if you want some more details on forward voltages and light-emitting diodes. So light-emitting diodes are just a subspecies of diodes in general that happen to emit light. Actually, a more common kind of diode is a silicon diode. It works much the same way. Instead of releasing that energy across it as light, it releases that energy across it as heat. But for everything else, things are essentially the same. Current only flows in one direction, right, from the anode to the cathode. For a silicon diode, the voltage drop, instead of being in the 2 to 3 to 4 volt range like we were talking about with light-emitting diodes, a forward voltage drop is about 0.6, 0.7 volts, something like that. I usually think of it as 0.6, 0.7 depending on temperature. And if you're looking at the physical devices or the diode symbol here, the line is on the cathode side, the negative side. So here, I have some diodes here I can show you. They come in many flavors for many applications. We won't actually be using diodes directly tonight, but I want you to understand what a diode is. When you see that symbol in the transistor, you know what we're talking about. So this is a generic diode here, and you can see just on this side the little silver line there. So I know that side of my diode is my cathode side, my negative side, my downstream side. Similarly, I have some little multicolored diodes here that have a black line on one side. That black line is going to be the negative side, or the cathode side more properly. So that's what a diode is. It's not going to be super germane to our conversation, but when you see that arrow, just know that there's a diode, and that current can only flow across it in one direction. So inside of these symbols for the NPN and PNP transistors we were just looking at, we have this diode. And you'll see in both cases it is between this base terminal and the emitter terminal. In the case of an NPN transistor, current will then only be able to flow between the base and the emitter, and not from emitter back to base. And similarly, for a PNP, current will only be able to flow in the direction of this arrow from the emitter to the base, and not backward, right? It's a diode in there, basically. It's not a separate little diode floating around. It's part of the silicon structure of the transistor itself. But when you're thinking about the way that current might be flowing through this transistor, know that that arrow is there to help you out. So here is the fundamental idea of how transistors work. And by fundamental, I mean a good enough understanding for, at least for me to make things with and for you to make things with, not to go out and build your own transistors, although that would be a super cool project. But this is how you can think of them in order to get them working for you. For both species of transistor, NPN and PNP, a small current between the base and the emitter allows a large current to flow between the collector and the emitter. right? I'll say that again while drawing things with the mouse here, right? If I have a setup that creates a small amount of current flowing along this diode, along this base emitter diode from the base to the emitter, that's going to essentially open a switch, or close a switch, open the floodgates between the collector and the emitter to allow a large current to flow. For an NPN transistor, that looks like us putting a little bit of current into the base and it flowing down to the emitter, and that will allow a large current to flow from the collector down to the emitter. For a PNP transistor, things look just a little bit different. Remember we have this arrow pointing the other way here. For a PNP transistor, if we allow a small current to flow from the emitter out through the base, right, out through this arrow, out through this base here, we will allow a large current to flow from the emitter down to the collector, right? We're following the same direction of this arrow. So from emitter to collector in a PNP, from collector to emitter in an NPN transistor. If this is all sounding a little bit Greek, and I apologize if it is, right? We're throwing a lot of new terms and a lot of new symbols around here. We're going to get to an example in just a couple slides here, and I think that will start to clear up how we can actually make things work. Right? So it's another sort of visual symbol of how the inside of a transistor works. This is a classic drawing that you see sometimes of the transistor man, the little man that lives inside your transistor. And his whole job, you might see him here, he's watching a current meter that's on between the base and the emitter here along this diode. He's saying, oh, there's a little bit of current there. I'm going to make sure that the amount of current that can flow between the collector and the emitter is some multiple of that current between the base and the emitter, right? If Mr. Transistor Man sees 1 milliamp of current flowing from base to emitter, say, he might say, well, I'm going to turn down the resistance of my collector-emitter junction here so that 100 milliamps flow, or 200. Try and reduce his resistance between the collector and the emitter here to allow lots more current flow, some large multiple of the current between the base and the emitter. I do want to say this is a great drawing for sort of remembering what's happening inside of a transistor, but don't go thinking that there's actually a resistor inside your transistor. This is just sort of a schematic diagram to see what the little transistor man is doing. If you put a resistance meter on your transistor, it's not going to give you the answer like there's an actual variable resistor in there, but this is a decent metaphor for what's happening. So the transistor is going to provide us with this switching action that we were sort of looking for in our first idea of how we might provide a lot of current or a higher voltage to our loads. We're going to use our digital pin in our Arduino to provide or take in a small bit of current that's going to flow through the transistor, and that, when it flows, is going to open the floodgates between the collector and the emitter and allow a large amount of current to flow through our LED, our resistor, our heater, our motor, whatever high current load that we can't derive directly with our Arduino. We'll use our transistor like a switch to turn that flow of current on and off. Make sense? I want to introduce just a little bit more terminology before we get to any. No, let's introduce a little terminology, just because writing out things like the current between the collector and emitter and the current between the base and the emitter is going to make it really hard to show you some of the math that's important for this. So I want to introduce just a couple little pieces of terminology, and that's only to say, we introduced the idea last time that current is represented by the letter I in our equations. You might remember Ohm's law, V equals I times R. Well, in working with transistors, it's common to denote the current between two terminals by just writing in a little subscript here what the two terminals are. So the current between the collector and the emitter is I sub CE, right? The current between the base and the emitter is IBE, right? So that's just a shorthand way of saying the current flowing between these two small letters here is this I sub the two small letters. That sort of makes sense. I know there's a lot of terminology being thrown out sort of early, but it's going to make writing things down a whole lot simpler. Let's see what questions are coming up in the chat before we get into the examples. Chris asks, is there a little man inside them? Chris, as a props master, I would think if anyone's going to be able to put a tiny man inside them, I think it's going to be you. Yes, Ken says the resistor is fake, but the man is real. Yeah, so make sure to tip your transistors, but don't tip them over. So to use this terminology that you introduced here, right? This current being represented with these two extra letters, right? I said earlier that our transistor man is watching the current that's flowing between the base and the emitter, and he's making sure that the current between the collector and the emitter is some large multiple of that, right? So to say that another way, now that we have this terminology, the ratio between those two quantities, right? The little current we're letting in the base and the big current being allowed between the collector and the emitter is called the beta of the transistor, or sometimes H sub Fe. So if we were to write out what our transistor man is doing here, he's saying, oh, I have this base current here, I have this large collector current here. I'm going to make sure that my collector current, my current flowing between my collector and emitter, is some large multiple of the base current, this current between the base and the emitter. This beta is often in the range of 30 or 50 to 250, 350, 500, sometimes 1,000 or more. You can count on it being a large number, but you can't necessarily count on it being the same large number even between two resistors with identical types from this identical manufacturer. So for example, we're going to use a 2N2222 transistor from my junk box for our experiments tonight. If I pulled one out, this beta might be, at room temperature 100, and the next one I pull out at room temperature, it might have a beta of 200, and the next one might have a beta of 75. It has to do with manufacturing tolerances of the materials that these transistors are made of, and the tolerances generally are not very good, to the point that it's actually quite a bit of work for some specialty circuits that you need to have two identical transistors. It's actually really hard to get them to match each other, especially because this parameter, this beta, as you might have guessed, changes with temperature. But what we're going to do is set up a situation where we can say, well, as long as that beta is pretty big, 50, 100, which we can sort of count on it being, then that will be sufficient. And then if it ends up being extra large, when we are too forgiving, that transistor man really is like, I'm just going to crank this, we're going to let a lot of current pass if it wants to, then that will be fine. We're going to use these basically, if you think about using these transistors as a switch, which is what we're going to be doing, we want that switch to either be open and passing no current, or closed, passing a lot of current. And so we're going to set up a situation that even if this multiplier is not quite as high for some transistors as others, it's still plenty big to close that switch, if that makes sense. So I wanted to introduce the idea of beta in a transistor, this ratio between the small current and the large current, because you're going to see it pop up sometimes as you're looking at transistors. To show you the drawing of what this looks like for a PNP transistor as well, right? For our NPN transistor, this base current flows out of the base down into the emitter. For our PNP transistor, it flows from the emitter down into the base, right? It's always just following this diode, following this arrow, right? So just something to keep in mind. All right, so let's do an example using what we know now. I think if you're a little bit lost, that's totally fine. We're going to do an example, and that will help it make sense. So for our example, we're going to use this little red light bulb that we made use of last week. I think this was either our proton or electron when we were talking about voltage. It might have been both at some times. This is just a little cheapy 4-watt 12-volt bulb that I bought. Here, I still have the package down here. I went to Menards and I bought some cheapy bulbs to play with. So we had something to work with. And it told me that this bulb was a 12-volt, 4-watt light bulb. If I put 12 volts across it, it's going to emit 4 watts of light and heat and power. So I'd like to drive this with an Arduino, let's say. But of course, I can't supply 12 volts of power. And as we'll see, I can't apply enough current directly from the Arduino. So we're going to use a transistor to drive this light bulb. So let's start by figuring out, we know 12 volts is too much. Let's figure out how much current we're going to need to pass through our transistor to be able to drive this light bulb. So like I said, it's a 12 volt, 4-watt light bulb. Oh, it was Home Depot. I think I said Menards, I meant Home Depot. Neither are sponsoring this video, so I don't think it matters. So to figure out how much current we're going to need to put through it to be able to turn it on, we're going to think back to that equation that we learned last week, this P equals I times V equation, the power equation for electrical power. And we know the power is 4 watts. We know the voltage is 12 volts. So if we divide through by 12, we see that we're going to pass 1/3 of an amp, or 333 milliamps, through this light bulb when it's on at full. That's quite a bit more than the 20 milliamps we can safely put out of an Arduino, which is partly what's motivating me to want to use a transistor to drive this. So here's the circuit that we're going to start by setting up. I've got a 12-volt power source. I'm going to use my bench power supply for this example. You could use an old computer power supply or a wall wart power supply, for example. Anything that'll supply at least 300 milliamps would work. And I'm going to connect the transistor like this. I'm going to connect the collector of my transistor directly to my light bulb. I'm going to connect the emitter of my transistor to ground. And let's see, let me get my circuit over here. I found, this was sort of by chance, I found that the pins on these light bulbs can be shoved directly into a breadboard, which is kind of handy if you straighten them out a little bit. So that's a very helpful thing. So I have my light bulb here, and it is plugged directly into my breadboard. You can see that one side of my light bulb is plugged into this power rail over here where I'm going to hook up 12 volts in a sec. You can ignore the motor hooked up over here, spoilers. You can see the other side of my light bulb here is connected through these two wires to this position on my breadboard, which is connected to this little guy, which is, in my case, a P2N2222. It's a little NPN transistor. In our case, we'll talk a little bit later in the night about how to choose a transistor for a specific project, but in my case, I've verified that I can pass, a few hundred milliamps through it for a short amount of time. This is sufficiently big, right? So that's the first part of our hookup that we're going to do. So remember that to turn this on, I'm going to want to put about 300-ish milliamps through here. And if I'm being a little bit vague about the math, it's because, remember, this is a light bulb, right? It's a glowing piece of tungsten. I'm not going to expect that the manufacturer has made this exactly a 4-watt light bulb. It's going to be 4 watts-ish, 4.5, 3.5, who cares? It's a tiny, shitty light bulb. So when I do all this math, I'm going to do it all with a little bit of, I'm going to do the math precisely and then apply kind of a fudge factor to make sure that, all the things are going to work in the end. So I want to be able to pass about 300 milliamps through this light bulb. So we said earlier that to allow this transistor to pass, a 300-ish milliamps between the collector and the emitter, we need to supply, let's say, about 3 milliamps between the base and the emitter. For doing calculations like this, assuming that your ratio between these currents is 100 is a pretty safe place to start. And we'll see in a little bit how we can actually ratchet that up some to make sure that we're really getting that switching action that we want. But to make sure that we can sort of start things off right, let's assume we need to put 3 milliamps of current between our base and our emitter. And for our purposes, I'm going to assume that we're going to drive this with an Arduino, because that's sort of the whole point of these streams. So our supply voltage on the sort of this base side here, let's say, is going to be 5 volts, right? We're going to use a digital pin, we're going to turn it on and off. So let's say we have 5 volts here, and we want 3 milliamps to flow across this base and emitter here. So what size resistor do we need to put in between 5 volts and the transistor to make sure that only 3 milliamps of current flows? Well, if you think back to last week, we learned an equation that will let us figure this out. This is Ohm's law that we learned last week. Voltage equals current times resistance. And this equation should look very familiar. If it doesn't, I encourage you to go back and watch last week's stream. We're going to just work through the math. So our voltage, right, our 5 volts here is what we're starting with. We once again, much like when we were working with LEDs last week, we lose some voltage running it through this diode, right? For our LEDs, it was 2 or 3 volts. For our silicon diode here, it's 0.6 volts, give or take, right? So we have 5 minus 0.6 equals our current, 3 milliamps or 0.003 amps, times our resistance. We move things around and we find that our resistor should be about 1500 ohms. So if we put a 1500 ohm resistor between our digital pin, our 5 volts here, and our base, we should get about 3-ish milliamps of current flowing, right? So yes, so here's we put our 1500 ohm resistor here, we get our 3 milliamps of current there. So this is the circuit that I'm going to wire up here on the breadboard. I've got my 12 volts applied to one side of my lamp. The other side of my lamp is connected to the collector of the resistor. The emitter of the transistor is grounded, and I have a 1500 ohm resistor between digital pin 13 and the base of the transistor. Digital pin 13 is just an arbitrary choice, could be any digital pin, but that's going to let us use a bit of code I wrote earlier to test this out. So let's go to the table and get this wired up. So grab my Arduino here, and first things first, I am going to wire digital pin 13. Where's my bit of wire? Here we go. Here we go. So this is going to be connected to the base of my transistor here. I'm going to put that into digital pin 13. And I want to make sure that I also connect one of the ground positions on my Arduino to the ground position of of my circuit here. You actually see, I think I drew it into the circuit diagram here. Yeah, you want to make sure that all of the parts of your circuit share this common ground so that we have a full, if current is going to flow from our digital pin into our transistor, then, you may have heard that current always needs a return, like electricity has to have a full circuit. This grounding, these are both connected to the same ground point, make sure that we have that full circuit of current flowing. So I'm going to make sure that I take a bit of wire into one of the ground positions on my Uno here. There we go, and I will connect that to the ground rail just there, right? So there is my circuit, and then I already have a 1500 ohm resistor connected, just that little guy down in there, between the base and the emitter. Between the pin of the Arduino and the base of the transistor, right? Because we want to be able to limit the current from the Arduino going into the base of that transistor. Right? So let's get this side plugged in, and we'll run a little code, and we'll fire it up. The code I'm going to use here, let's pull that up first. Helps if I launch the Arduino IDE to run this with. The code that I'm going to use to do this transistor example is the most basic example there is. We're just going to use the blink sketch from the examples folder in our Arduino IDE, which is just going to turn pin 13 on and off, one on for a second and off for a second. I should say, as always, the code for all of this is on the website, jeff.clash/electronicsbash. But you can also, for the sake of this example, just go to File, Examples, Basics, and open the Blink example if you're playing along with this at home. So I'm going to plug in my Arduino, and I'm going to make sure that I've selected the right port and the right board from my Tools menu. It looks like I have. I'm going to hit Upload. I'll come back to the table here, and we'll see if things work. Compiling over here. Looks like my code is still compiling. Oh, there we go. Now we're uploading. There's also a decent chance that as I've been setting this all up... Oh. Chris, you nailed it, just as I was thinking it. As everyone knows, I am habitually awful at remembering to turn the power supply on to make these things run, which I, of course, have not done. So thank you, everyone. 10 points to Gryffindor for everyone who thought that I would forget that. So I'm going to take the two leads of my power supply here and make sure off camera here that my power supply is set to 12 volts. There we go, 12 volts-ish. And there's also a decent chance that, as I've been moving things around, something has come unplugged, which we'll see if this fails. Ooh, that's a good sign. There we go. So now I have my light bulb turning on for 1 second and off for 1 second. And actually, if you look up here, this LED on the Arduino is also connected to pin 13. So we can tell when that pin turns on, it turns the transistor on, which allows current to flow between the collector and the emitter. So that current has to pass through this light bulb, and current flows. Yeah, everyone, it seems, called that I was going to forget to turn the power supply on. That is not going to be the last time tonight that this happens. If we're lucky, I'll remember to turn the power supply voltage back down before we do the 5-volt demos, or things will get a little smoky. But, just a little Sunday night excitement for all of us. So now that we have this nice thing blinking here in the background, let me answer a couple quick questions. Oh, Travis's question, which Kenneth alluded to the answer to, why use a PNP versus NPN, is a really good question. We're going to do examples with both of them tonight, and I'll show you why you'd want to use one versus the other. There we go. So this is the basics of using the Arduino to drive a transistor to turn a higher current load or a higher voltage load, or in our case both, on or off. You take usually a digital pin, or could be an analog output pin from an Arduino, through a resistor into the base of a transistor. That's going to supply a little bit of current. That's going to allow a large current to flow between the collector and the emitter of your transistor, right? Using that transistor as a switch to allow a large amount of current to flow. Palmer says there's a high frequency noise in your audio when the bulb is on. Oh, that's unfortunate. Oh, that's so funny. I have a metering in my ears and I can't hear it, but it's probably, I wonder what frequency it is. Because the Arduino is doing pulse width modulation at about 500 hertz, but if it's high frequency, it's probably not that. It might be coupling back on the USB of the things. That's really good to know. I hope it's not too obnoxious, but maybe for the time being, we'll just unplug that. Palmer is a professional audio human as well, so the fact that he's the one who pointed out the audio glitching is not surprising to me. Kenneth says he can't hear it. Palmer, you might be working with some, this is about 13,000 hertz. Palmer, you might be working with some higher fidelity reproduction equipment than some of us out here for sure. Yeah, I'm so glad we've gotten to this point, because this is really fundamental. Using a transistor like a switch to turn something on or off to provide some extra current or extra voltage possibility, right? You know, when I say current or voltage, this is a lamp that requires 300 milliamps of power. This could be a 12-volt lamp that requires 20 milliamps of power, but because we can't provide that 12 volts to this lamp, we would, excuse me, use a transistor in that case as well, just to make sure that we're providing the voltage that the lamp needs. Yeah. Questions on that? Feel free to drop them in. I'm going to carry on just clarifying a few things about this example, but it's really key that you understand how you use this transistor as a switch. Use a little bit of base current to, essentially close the switch, allow a lot of current to flow between collector and emitter. What we're essentially doing is driving the transistor into saturation. So what we've got here is a little graph of the voltage across the bottom here between the base and the emitter, right? We're applying a slightly higher and higher and higher voltage. And here we have essentially the voltage across that base, the voltage across the collector and the emitter, right? If that voltage is high, that transistor is resisting things flowing. It's holding itself at a high intermediate voltage. And when it turns on, like closing a metallic switch, it's going to let the voltage across itself, the resistance across itself, become very, very low, right? So this is essentially a graph showing that, right? As we increase the voltage across the base, at some point we start to get current flowing across that diode. And by the time that our voltage is high enough and our current is high enough, we have saturation. The transistor is as on as it's gonna be. There's a point of diminishing returns, right? It's never going to, it's always going to have a little bit of resistance across it. It's never going to turn more on. When we get to this point when the transistor is as on as it's gonna be, that's called saturation. And so essentially what we're doing here is making sure that we're driving our transistor into saturation every single time we use it. We want to use it as open or closed. We don't want some intermediate state where it has some intermediate resistance or something like that. We want to saturate that transistor. For my particular transistor, the P2N2222A, and probably the ones in your kit, the 2N2222, that saturation voltage, that voltage that's across the transistor when it's as turned on as it can be, is usually no more than about 0.2 or 0.3 volts. And when I say the voltage across that transistor, right, that's voltage that we're losing in that part of the circuit, much like we lose voltage in a diode. You can see I snipped the little, I wish I could make this little thing go away. I snipped a part of the data sheet for my particular transistor out, right, which has this this note here: collector emitter saturation voltage is a maximum of 0.3 volts when I have a base current of 15 milliamps and a maximum of 1 volt at 50 milliamps. But it's probably going to be a lot less than that. For most practical purposes, you can assume it's between 0.2 and 0.3 volts. So to go back to our transistor man, when we've applied enough base current here, transistor man is going to turn down his impedance, his resistance to current flowing between the collector and the emitter, until he really is saying, hey, I've got to maintain a voltage drop here between this collector and the emitter of 0.2, 0.3 volts. I can't go any lower than that. But once we're to that point, that's as low as we're going to go, right? So as long as we're saturated, we have closed that switch. So that's just all to say, we calculated that putting 3 milliamps through our base was going to turn our transistor on enough to power this particular lamp. But there's rarely any harm in driving your base harder than that. All it really does is guarantee that, if your transistor has a lower beta, it doesn't have that high of a multiplier, is a little out of spec, is a little bit too cold, that it's definitely going to saturate, that it's definitely going to close that switch in a way. So while we can make do with 3 milliamps of base current, why not use all 20 milliamps that we have from a digital pin? At least in my case, where I'm just plugged into a computer here, I might as well make use of that current. If you were doing this in, say, a battery-operated situation where every milliamp counts, yeah, you might want to be specific about how much base current you actually need. But for our purposes, especially when we're plugged into a computer or plugged into the wall, we're just going to make use of all 20 milliamps. So let's run the numbers one more time, assuming not that we need 3 milliamps, but 20 milliamps. And we run this through Ohm's law again, and we divide everything out, and we see that a 220 ohm resistor is basically what we need to give ourselves about 20 milliamps of current through the base down to our emitter here. So That's going to make sure that our transistor, even if things are a little squidgy, even if our math's a little bit off, even if our transistor is a little, on the lower beta side of things are still going to work. So you'll see this circuit looks very familiar, except I've reduced my resistor here from a 1500 ohm resistor to a 220 ohm resistor. So before I plug it back in, because it sounds like it makes an awful noise for some of the audio techs out there, I'm just going to replace this 1500 ohm resistor with my 220 ohm resistor that I prepared earlier. Make sure I plug this in correctly. There we go, between the digital pin of the Arduino coming in on this black wire here and the base of my transistor, which in my case is the center pin. That looks right. Plug that back in. Power supply is still on, so points to me. Hi, y'all. Hi, Becca, and thank you for joining us tonight. Ken says, I don't like to use all 20 milliamps since that means you don't have any current left for the attached LED. That's true. On pin 13 here, I have this little LED drawing a little bit of current as well. Do you always have to use two power sources when you have a circuit with a transistor? No, and we're actually going to use, we're going to do an example in a little bit where we power a 5-volt motor off of the 5-volt rail on the Arduino. Ken says usually it's a 2 to 3 times factor on the calculated 3 milliamps. Sure. So, the way I think about it is like I have 20 milliamps, I might as well drive it hard. Ken says, if I calculated 3 milliamps, maybe 6 or 9 is good. Oh, thanks, Becca. Yeah, I'm having a really good time here. Feel free to ask questions. You're jumping in hot and heavy here, but we have only a couple of topics to get to tonight, so I think we can dive in depth into them if we want to. So, to show you the circuit that we're working on now, right, this is our basic drive a thing with an NPN transistor from an Arduino. And this circuit is really fundamental, right? You could do a lot with this circuit. You can choose a bigger transistor. We'll talk about choosing transistors in a little bit to drive a lot more current or a lot higher voltage, right? If you're looking for a way, if you came to this stream tonight thinking, man, I hope I come out of this knowing how to turn on a low voltage light bulb with an Arduino, here you are. Take the circuit down. The slides, of course, as I said before, are on the website, jeff.glass/electronic-bash. Download them, take this circuit, use it. It will work well for you. One thing about this circuit is we're sort of, trying to lock this into our head and understand why it is the way it is. Because I kind of just said, this is how we're going to do the circuit, right? Trust me, wire it up, and it works, which is great. Here, I'll unplug this for Palmer's sake. Why is this circuit wired up the way it is? In other words, why is the transistor down on the negative side of the light bulb? Why is it down here and not on the upstream side, right? This is a good configuration for this NPN transistor. This is a bad one. Good, bad, good, bad. Why is that? Well, let's think just a little bit about what we already know about transistors, which is to turn them on, we need current to flow through this base emitter diode, right? I need to force just a little bit of current through that base and that emitter, which means, from what we know about current flow, that the voltage on this base is going to have to be higher than the voltage on the emitter, because that's the way current flows, right? It's going to flow from an area of high voltage to low voltage. Well, when we want this light bulb to turn on, right, what do we mean by turning the light bulb on? Well, we want to put a bunch of voltage across it. It's a 12-volt light bulb. I want to have 12 volts or so present on one of its wires and 0 volts or so present on the other one. So for this light bulb to be on, as much as we want it to be, I need to have 12 volts or so across this light bulb. Or in our case, let's say our transistor has a voltage drop when it's all the way on about 0.2 volts, right? When it's fully saturated, I'm losing about 0.2 volts here. So, let's say I have 11.8 volts left of the light bulb. Fine, we'll work with that. But if that's true, then to turn this transistor on, I would need to have the voltage at this point at the emitter, 11.8 volts, plus the voltage I need to overcome this diode, that 0.6 volts. So I would need 12.4 volts present on this base to even turn this transistor on, and that's actually higher than my supply voltage. It's way higher than the transistor, than the Arduino can supply, and it's higher than our collector voltage here, which is a big no-no. You don't want to put your base higher than your collector. That's a good rule of thumb, right? So I've created this circuit that I can't actually turn this on enough to make this light bulb do what I want it to do. So that's the reason for putting this NPN transistor on the downstream side, if you will, of this light bulb. Because in that case, right, to get current to flow through this diode, well, this emitter is at ground. It's at 0 volts, right? So to turn it on, I just need to get this base to 0.6 volts, 0.7 volts. Totally easy. We're going to get it to much, much higher than that, right? We're going to have a little voltage loss across this resistor, but we're going to be able to provide 0.6 volts to this transistor, no problem. So that's why when you're wiring up an NPN transistor to an Arduino circuit, this is the configuration you use. You have your power supply, your load, in this case a light bulb, and your transistor is on the downstream side. You'll often hear about hearing things being switched on the downstream side, or sometimes low side switching on the side of the lower voltage. And with an NPN transistor, that's essentially what you're going to do all of the time. Does that sort of make sense? I hope so. Sorry, I was getting a little parched there. I needed a little break brought to me by Alley-Time Pale Ale from Spiteful Brewery here in Chicago. Oh, I know I say it every week, but I'm so delighted by the range of craft breweries that are here in Chicago. I think we haven't duplicated one yet, and that's going to be kind of a goal, I think. Just so good. Lee says, are transistors only for DC circuits? The circuit that we're looking at here, where we have a load and a transistor and ground, this is meant for a DC situation where you always have a positive voltage on the upstream side of the load and a ground or a negative voltage on the other side of your load. There are ways to use transistors to switch AC circuits, but they're somewhat more complicated. Let me put a pin in that and talk to you about it a little bit later when I've introduced the other kind of transistor, which is a PNP transistor. Typically, if you were going to turn AC circuits on and off, these wouldn't necessarily be the right tool, because if you think about this, right, if I have a DC circuit, right, where I always have positive up here and ground or negative down here, then this relationship of like where the current is going to flow between collector and emitter stays the same. If I had an AC circuit where those things were going to flip and I had a positive voltage up here on my emitter, say, and this was grounded, there's no way I'm going to be able to get current to flow back through this diode to turn the transistor on. So this circuit, at least, is not good for an AC circuit. Good question. Christina asks, are Spiteful sponsoring me? No. No, I really wish so. I don't know if they're watching. Spiteful Brewery, if you're watching, you make a very tasty Alley-Time Pale Ale here in Chicago, Illinois. All right, enough shenanigans. Never enough shenanigans, but let's carry on with other things while we shenanigans. So this circuit, like I said, is a really useful circuit. And this load doesn't have to be a light bulb. It could be an LED, it could be a light bulb, it could be a heater, right? Something we just pass current through and gets hot. It could be a DC motor that we put current across and it gets hot. This is a really useful circuit. NPN transistor, little base resistor connected to a digital pin, and your load put on the collector side. So keep this circuit in mind. Just to show you that, let me do another demo, which is very similar, except instead of controlling our light bulb here, we're going to use a piece of LED tape. If I can remember where I put my LED tape. I started it together just before this demo for exactly this purpose. If not, I'll do some soldering live, but I feel like controlling LED tape is a thing that we do with transistors a lot in Arduino land. I think it would be a useful thing to do. Did I drop it? Oh, I dropped it on the floor. Professional electronic streaming brought to you by Jeff Glass. So LED tape, for those who haven't seen it before, if you haven't, it's super, super cool stuff. And here's what it is. It is a flexible ribbon of a circuit board that has LEDs and resistors pre-soldered onto it when you buy it. You buy this stuff in a roll that's about 5 meters long, about 16 feet of this stuff on a go. And what they've done for you, which is really nice, is that they've pre-soldered these resistors on so that the tape is made for a specific voltage. And they say if you apply that voltage to these positive and negative connection points here, then the resistor takes care of all the current limiting math shenanigans for you for that voltage. Will just turn on. So this piece of LED tape that I bought a bunch of years ago, it usually doesn't come in this gold color anymore, said if you apply 12 volts to any of these positive and negative pads here, I'm just going to turn on for you. And that's awesome because this stuff is flexible, it's bendable, it's relatively cheap, and you can cut it every, I don't know, what is that, 2 inches? And it will continue to function. So this was a 5-meter section that I chopped off, I don't know, 4 inches of it here, bodged a couple wires on the end, and it's going to work just as well. If you haven't worked with LED tape, this stuff is awesome, and I encourage you to pick it up. This stuff is white. You can get it in multiple colors, blue, red, green. You can get stuff with multiple colors on the same tape. We could do a whole night about LED tape, and honestly, we probably should. But just to show you what it looks like, power supply still turned on. I'll just attach my power supply directly to it here. Ooh, I have some of it out in the middle. must have a loose solder joint. But you can see when I attached those 12 volts to it, those LEDs just turned on. I didn't have to worry about adding another resistor or anything like that. This stuff is awesome. Started coming on the scene about a decade ago, and it's gotten so cheap and so good. But to show you that you can control it with an Arduino, I'm going to basically put this in my circuit the exact same place the light bulb was. In this case, polarity matters. So just to show you the circuit diagram again, I'm going to make sure that the positive port on my LED tape is connected to my positive voltage, and the negative side is connected to the transistor in this case. So on the table here, take my red wire, my positive wire, plug it in there, take my negative side, plug it into the collector of the transistor. I'm going to plug my power supply back in, and I'm going to plug my Arduino back in. Apologies to Palmer's ears. Pull this over here. Here we go. Here I can zoom out. I have that power. And now you can see, much like the light bulb was doing before, now when digital pin 13 turns on, when the little LED turns on, the LED tape turns on as well. Piece of cake. Let me take some quick LED tape questions, and then we'll do another demo with it. Let's see. Ken says, pro tip, you'll be disappointed by the sticky back on LED tape. Yeah, using glue or 3M tape or epoxy is good, or the tape actually will stick pretty well to anything that's like metal and entirely smooth, but anything else, yeah, don't rely. This stuff has this, what Ken's referring to is this, you can peel off this label on the back here and you get essentially a sticker, but it's not terribly strong. Hot glue is good. Black hot glue is good if you're doing it in lighting sensitive applications. Michael Trudeau says hot glue doesn't stick well to some types of wood and some types of tape. Yeah, it's worth doing a demo. If you're going to do a big project with this, do a test first. VHB tape, VHB is a product from 3M. There's a multiple different types. There's a thin gel type and kind of a squishy or foam type. Stands for very high bond tape. That stuff is super good at sticking to, I would say, most things. It's a little bit pricey, but you can get it on Amazon. Their products in the VHB line are what they use to stick the windows to the outside of the Burj Khalifa tower. Because there's so much thermal expansion of those planes of glass throughout the day in that hot environment that mechanical connectors would fail. So they basically just use this sticky double-sided tape to hold the window panes in place. That fact, courtesy of Alec Thorne. Alec, I don't know if you're watching, but thank you for that fact. It's a great one. So this is how you control, basically how you control LED tape with an Arduino. You use a transistor to pass the current through it. I'm passing just a little tiny bit of current because there's a little bit of tape here, but this could be a significantly amount more. Let's see. What happens if you connect it to the wrong polarity? Why don't I show you? So I'm going to take my connectors out here. I'm going to hook up my positive side to negative and my negative side to positive, and the results are entirely underwhelming. It actually just doesn't turn on at all. And that's because this circuit here is essentially, we said that current can only flow one way through a diode. What I have here essentially is a series of diodes, so the current isn't going to flow back the other way. So nothing happens at all. You generally can't hurt anything by plugging it in the wrong way. Becca says, what's your favorite joint connector for LED tape? Ooh, yeah, Michael's right, soldering. If you have to do a corner, there are these little dinky, like, bite-on connectors that sort of bite onto one LED tape and bite onto the other. They all really suck, but what you can do is get the kind that has, it's a little flexible piece of circuit board ribbon and two bite connectors that you add to that. Throw the bite connectors away and just solder that corner piece of circuit board in place, and that will work pretty well. But beyond that, soldering wires is really the best way to go. We usually would do a solder joint and then a piece of like heat shrink adhesive, right? A piece of rubber tubing that goes around, you apply heat to it and it shrinks down nice and tight, and sometimes some hot glue on top of that is, I think, what I would recommend. Yeah, here, let me put this back in working orientation so we can do another demo with our LED tape here, because I want to let you know that not only is this how you turn on LED tape, but this is how you can dim LED tape as well. So I'm going to open up another demo here. This is just the basic fading example from the Arduino IDE. So if you go into File, Examples, I believe it's under Analog, Fading, right? You'll get this example here. I have to change which pin my Arduino is connected to. I'm connected to pin 9. And upload my code. And All this kind of code is going to do, we talked a couple weeks about using the analog write function to apply some pulse width modulation to simulate an analog value coming out of your Arduino, and that was used to dim a single LED in that situation. But the same code can be used just as well to dim something that's being controlled by a transistor. And you can see at this point that LED tape is being dimmed on and off, just like our singular LED was. And the reason that that works, you remember, up here, I'll pull up our diagram again. You remember from a couple weeks ago, we talked about pulse width modulation, right? Our way of sort of simulating an analog value using our digital circuitry, right? In our situation where our pin is entirely off, it just sits at 0 volts. When it's entirely on, it sits at 5 volts. And in between, it spends a certain percentage of its time either at 5 volts or at 0 volts. If it spends just a little bit of time at 5 volts and it's mostly off, then we're only going to see a little bit of output. If it spends most of its time on and a little bit of its time off, it's going to be mostly on. And sort of anything in between. And these are some visual examples of, oh, there you are. These are some visual examples of how pulse width modulation might look, right? For a 25% duty cycle, we're at 5 volts 25% of the time, and we're off 75% of the time, and so on, right? So this is what we were applying to a single LED, but for a transistor, this works just as well to turn our transistor on 25% of the time and turn the transistor back off for 75% of the time, or turn it on 75% of the time and turn it off 25% of the time. The transistor switching action well, really in all cases for the kind of frequencies we're talking about, which is about 500 times a second for the Arduino, the transistors are going to be able to turn on and off plenty fast to give you that same smooth dimming action that we were seeing with a singular LED. Cool? So if you're looking to dim some LEDs or some LED tape, putting it through a transistor is the way to go. Moving right along for one more demo. Oh yeah, so a couple weeks ago we did our evening talking about servo motors and stepper motors, which were kinds of motor, if you weren't with us that night, those were kinds of motor that you basically plugged into power and then used a kind of signal from the Arduino to tell those motors where to move. And I said I wasn't going to be able to show you a basic DC motor that you just squirt power into and it moves because we didn't have the tools yet, and the tool that we need is a transistor. So let me get this wired up. I'm going to turn my power supply down to 5 volts for this demo before I forget and turn it off. So place your bets now as to whether I'll remember to turn it back on. And I'm going to use this little DC hobby motor. These come in all kinds of flavors and sizes. This is one from a junk box from ages ago, but they're all essentially similar, right? I have 2 terminals here that I've bodged some wires onto, and I have a little tiny output shaft. This is meant for going, I think, in a solar-powered car or something like that, some kit I used to have. And I put a piece of blue tape on it here because this shiny silver shaft here is a little bit hard to see on camera. So the way that these work is you put current across them and they spin. In fact, here I can just, again, do this with just our power supply first, in case you don't believe that these things behave how I say they will, which is fair. Oops, I'll plug that back in. Come on, plug, clip. There we go. You can see with power applied, the motor spins. Get on there. Get on there, clip. My poor little clip has been somewhat abused in the past few weeks as I've been doing all these demos. But you can see I put power across it and the thing spins. And actually interesting to know that we'll make use of later, right? If I have connected red to red here, I'm spinning counterclockwise. If I put things the other way, let's say black wire from my power supply to red, things spin clockwise, right? So I reverse the direction of my electric current and the motor spins the opposite direction. We'll see how to accomplish that with an Arduino in just a little bit, but first I want to show you this just working on our existing transistor demo. So I'm going to plug in my red to my positive side here. I'm going to plug my power supply in here, and you'll see once again, here, I'm going to plug this back into pin 13. I'm going to run that blink example again. So we're going to turn the Arduino on for 1 second and then, turn digital pin 13 on for 1 second and then off for 1 second. Oops, can't open COM5. Why would that be? Getting a classic error as we are. Error, upload. There we go. Uploading. There we go. So come back over to the table. On for 1 second, off for 1 second. There we go. Right? So again, just driving a motor intermittently by using a transistor. So that same circuit that we looked at earlier where we had a load, an NPN transistor with its emitter grounded, and a single resistor is a really easy way to drive a lot of common DC loads. That's mostly what I wanted to show you with that motor example. So now that we've done that, I teased a little bit what the next section is going to be. Namely, one thing we might want to do if we have a DC motor in our circuit is to reverse its direction by reversing the polarity on the motor. So what we have right now is, I have this 5 volts hooked up to one side of my motor connections, and the other side is connected to ground. And to reverse the direction, I would somehow need to get this side connected to 5 volts and this side connected to ground. And it doesn't seem quite like we have the tools to do that. Because when we think about this, we're really just, allowing current to flow or not, but we're not reversing connections in any way. We're going to need some more tools in our toolbox. And one of those tools is going to be the PNP transistor. And this is going to go back to Travis's question from earlier, why would you use an NPN versus a PNP transistor? Well, we'll see when we look at how a PNP transistor is used. So just a refresher, right? PNP transistors, they work very much like the NPN we've been playing with all night. We allow a little bit of current to flow through this diode, right? Or we make that possible, and that's going to allow a large current to flow through the collector and the emitter. In the case of a PNP transistor, the current flows from the emitter to the collector, typically. If you can't quite remember that, it's just they're flowing in a similar direction to this arrow, right? So for a PNP transistor, we're going to let a little bit of current flow along this arrow to the base, and that's going to let a large current flow from the emitter to the collector in this direction. So for the purposes of our demo, I'm going to use this 2N3906 transistor. I just wanted to show you what it has. I also wanted to show you that when you look at their data sheets online, when I Google 2N3906 datasheet, this is the symbol that comes up for it, which feels upside down, but really what I'm going to take away is that the pin 1 here is the emitter, pin 2 here is the base, and pin 3 is the collector, right? Always make sure that you know which of those 3 is which for your specific transistor. So this is the circuit that I'm about to wire up on the Arduino. I'm going to walk you through it real quick first. I'm going to hook up the emitter of my PNP transistor to 5 volts up here. I'm going to hook up the base back to digital pin 13 through that same 220 ohm resistor. And then I'm going to connect my motor to the collector down here, and the other side of the motor will be connected to ground. So let's think for a second what's going to happen here when we run some code that turns pin 13 on and off. If pin 13 is if pin 13 is low at 0 volts, that means I have 5 volts here, I have 0 volts here, so current's going to flow through this diode, through this resistor, right? So not too much current's going to flow, just those 20 milliamps like we want, right? We're going to allow a little bit of current flow here, and that's going to let a lot of current flow here and flow through our motor and turn it on. So let's get that set up. So I've got over here on the other half of my breadboard, I ordered another pack of breadboards this week because I realized I'm running out of space to do these demos each night, but that hasn't quite arrived yet. So I'm going to use my cheat sheet here, make sure I'm getting this connected correctly. So my collector is pin 3 is grounded. Something is not right here. Something is quite wrong. That is positive voltage. Oh no, that's correct. Yes, and then this is connected through our motor. There we go. Okay, there. So I've got, zoom you in a little bit here. I've got my my emitter of my PNP transistor here is connected to power. I'm going to connect those power rails up again. This white wire I'm going to plug into my Arduino, and it's connected through that same 220 ohm resistor to the base of our PNP transistor, and then I'm going to connect through the collector of the transistor back to ground. So if that's a little bit hard to see on the camera, I know this is the circuit that I'm going to be making up, right? Emitter connected directly to 5 volts, base connected to a digital pin through a resistor, and collector connected to the motor, motor connected to ground. I'm going to, power supply is turned on. We're like 4 for 5 tonight, or 3 for 4 in terms of turning that back on, which is pretty good. And I'm going to need to, of course, plug in this wire back to pin 13 here so that the right half of the breadboard does something. Turn this on. And now we'll see we have something very similar but subtly different to what's happening before happen over here. You remember that, oops. Well, now we have nothing happening over here, which is not a feature. I think I'm just gonna, I've got a loose wire. We had before when we had an NPN transistor circuit, when the LED was on, the motor was moving, and when the LED was off, the motor is not moving. And now, if you look, we actually have the opposite. When the LED is on, so when the digital pin is high, the motor is stopped. And when the LED is off, or the digital pin is low, the motor is moving. And that's a consequence of just the way that current flows through a PNP transistor, right? I need this digital pin to be at 0 volts. I need current to be able to flow into it to turn this transistor on. And then when I turn this pin high, when I set it to 5 volts, well, I have 5 volts over here, I have 5 volts over here, so no current is going to flow. So this transistor is going to turn off and the motor is going to stop moving. So when you're working with PNP transistors, just remember that, I know I have been fairly casual about saying high is on and low is off, but in this case, it's important to remember that high means 5 volts present at the Arduino and low means 0 volts present at the Arduino, because that's going to affect how this sort of thing functions. Make sense? In this case, so I specifically chose a 5 volt, you're over here, I specifically chose a 5 volt load for this example because unlike the circuit we were just working with, if I was trying to drive a higher voltage load, I would have a bit of a problem, right? If I had a 12 volt load, like a 12 volt motor or that LED tape we were just working with, right? If I needed to have 12 volts here, well, then to turn this transistor off, I would need this base to also be at 12 volts, right? If I want no current to flow across this diode here to turn this thing off, I need this base to be at 12 volts. But the Arduino doesn't get to 12 volts, it only gets to 5. So no matter how high I push this pin, we're always going to have current flowing here, and so this load is always going to be on. The motor's going to be moving, the LED tape's going to be on. So directly driving a higher than 5 volt load with a PNP transistor from the Arduino is not possible. There are ways to do it, and for the purposes of tonight's example, we're not going to go super deep into them because it's honestly kind of an unusual situation, right? For most loads that you're going to drive, this circuit where you're driving, the switching on the downstream side and using an NPN transistor is going to be sufficient for most of the things you do, and honestly a lot more common. But just in case, I don't know what kind of weird shenanigans y'all will get into. So I wanted to just let you know that there is a way to do this, and I'm not going to go super deep into this, but just to give you sort of a vague sense of how it might work, you can use an NPN transistor to drive a PNP transistor in what's called a cycle pair. Again, I wouldn't worry about this too much. I just want you to know that this idea is out there, so when you run into a situation where you have some piece of gear that you don't have access to switching on the downstream sideway, and you have to use this PNP transistor setup to drive things on the high side to supply voltage to it, there is a way to do it. Basically, use this NPN transistor to turn on and off this PNP transistor. Don't bother memorizing this. Go Google it when you need it. It's Google, how do you control a PNP transistor with an Arduino when you need the solution? I just want you to know it's out there. Cool? So, to return us to our... Travis says, this seems ridiculous. Yeah, it's one of only many multi-transistor configurations that you might run into. I don't think I've included too many of them just because it's a little bit cumbersome. And honestly, for a lot of the kind of switching applications that we're doing, using an NPN transistor is going to be the way to go. But there are situations when a PNP transistor is going to be useful, like this DC motor conundrum that we came up with, right? We needed a way to, apply... Oops, let me turn this off here. To apply 5 volts to one side and ground the other to turn in one direction, and then to ground that first side and apply 5 volts to the other to move in the opposite direction. I said we were going to need some PNP transistors to do it, and this is how. And this is maybe going to look a little bit overwhelming, but we'll walk through this configuration because it's a good thing to understand. We're going to use a configuration called an H-bridge. Let me just blow that up a little bit here. So, this configuration is going to make use of 2 NPN transistors and 2 PNP transistors to do exactly that kind of switching action that we were just talking about, to apply 5 volts and ground to spin one way, and then reverse to 5 volts and ground to spin the other way, right? So, let me give you an example. If I turn on this top left PNP transistor and this bottom right NPN transistor, current's going to flow like this. I'm going to have 5 volts here, going to flow out and going to flow down through this NPN transistor, right? So current's going to flow one way. If I instead turn on the other PNP transistor and the other NPN transistor, current is going to flow in the opposite direction, right? So in this way, we can see by choosing which of our transistors to turn on, I can choose which direction the motor is going to spin. You wouldn't want to turn on two transistors on the same side of the H-bridge at the same time, because then you have nothing limiting the current flowing from 5 volts to ground, and things will get very hot very quickly. So I'd like to show you this configuration. This, I think, is the most complicated transistor configuration we're going to work with all night, but I hope it basically makes some sense, right? We're going to use a PNP transistor to inject some current into one of the wires of the motor, and then we're going to ground the other wire using an NPN transistor, and then we're just going to switch which of those wires has an NPN and which has a PNP connected to it, right? So if you're following along at home, this code is also on the website. This is the H-bridge demo. It will take me just a second to get this wired up, because I think I once again reusing a setup and a breadboard. But unplug that here and pull over. Thankfully, I don't have to build it from scratch. I built my H-bridge ahead of time, so you don't have to watch me plugging in things individually. So you can sort of see the symmetry of this circuit on the breadboard the same way you see it in the circuit diagram. I have my two PNP transistors up here with my red power wire going into them. I have my two NPN transistors here with my ground wire going into them. And these four colorful wires, these four DuPont wires here, are going to be my signal wires that I'm going to connect to the digital pins of my Arduino. And I think, when I built this before, I taped my wires together so they get plugged back in the same order, so that hopefully things don't go kablooey. So much like before, I need to make sure that the ground point on my circuit, right, so this ground point down here where these NPMs are connected, I want to make sure that that ground point is also connected to the ground on my Arduino. Right, we always have to have a shared ground so that current can sort of flow in a complete loop. All right, so there's that. That's grounded. And now I'm going to hook up my power supply and turn it on this time, I swear. Let's see. Ken says, when I'm playing with H-bridges, I like to put LEDs in the base pins too, so you can see which LEDs are on. Yeah, in fact, no spoilers, but if you remember from a couple of weeks ago when we looked at servo motors and stepper motors, and I showed you this guy, this whole configuration, which was an L293 servo motor driver, and I said, just hook it up like it's in the circuit diagram. This is, in a single package, an H-bridge. This is exactly this configuration with 4 transistors built into it. And what they've done for me here is, put it in a nice package with some terminals and a big heat sink in case it gets too hot. But that's exactly what we're building with individual transistors here. So if you're looking to use one of these to control a circuit, you can either build them up from scratch, and I encourage you to try it, right? It's a really good learning experience. Or if you go on Amazon and look at H-bridge module, you will find something packaged up just like that you can make use of as well. So let's finish hooking this up. I'm hooking this up to power, and I'm hooking up my motor. Make sure I hook that up to the right points. I'll hook my motor up to one side of my bridge here, and where did I have this hooked up last time? Other side of my bridge, just there. I think that's correct. Looks correct. So I'm going to load up my H-bridge code, get this spinning, and then we'll talk through the code just so you see what is happening. Plug this back in. Let's upload first, just so there's no hanky-panky. I don't quite remember what code is running over there at the moment, but I'd hate for it to be doing something it's not supposed to be doing. Let's see. Let's turn that power supply on. If things get smoky, then we'll turn things off. But hopefully, what we should see is, yeah, there we go. So now I have the motor spinning in one direction for 1 second, and then reversing and spinning in the opposite direction for another second. So we're using that H-bridge configuration that we were building up to supply 5 volts and ground in one orientation, and the reverse and supply 5 volts and ground in the opposite orientation. So H-bridge, a super useful circuit if you ever have to reverse polarity on something. If you've ever used a bicolor LED where passing current through one way is, say, green and the other way is red, using an H-bridge is a really easy way to reverse the current flowing through a bicolor LED like that. So if you have a multicolor LED, I know Megan Snowder last week was asking about like red, green, blue LEDs. Those often have not 2 terminals, but 3 or 4. So you don't necessarily have to reverse current in them. You just have to choose where the current is going. So H-bridge might not be applicable for that. But for driving a motor or doing something where you have to reverse the current, an H-bridge is the circuit for you. Just because we haven't looked at much code tonight, let's look at the code that's running this H-bridge so you get a little bit of an understanding of what's going on. So it's not terribly complicated. What I've done up here, we're going to have to sort of shift gears a little bit, right? Because we really haven't been thinking in code mode tonight. But let's take a little bit of a look at some code to understand how this H-bridge is being driven. So I defined an array of integers up here, right? You remember an array just holds up a list of values, right? I have my 2 pins that are connected to the bases of my PNP transistors, and I have my 2 pins that are connected to the bases of my NPN transistors. And I should remind you, this code is on the website, jeff.glass/electronicsbash, if you want to follow along in real time. And I made a note to myself, pins in the same position in each array represent transistors that can be on at the same time, that are on the opposite sides of the motor, right? So if I turn on pin 8 and 10, I'm going to have current flow one way. If I turn on pins 9 and 11, then current's going to flow the other way, right? I could have arranged this in the opposite orientation. I could have said to myself, like, I only want 8 and 11 on at once, but the way I chose to arrange it was so I should always have, you know, the first pins on and then the second pins on. In my setup function, I'm going to use our very familiar pin mode function to go through each array, right? I'm going to use this for loop that we learned about a couple weeks ago to go through the values 0 and 1 for this variable I. I'm going to say that the PNP number 0, right, because our lists count from 0. PNP pin number 0 should be an output. PNP pin number 1 should be an output. NPN pin 0 should be an output. NPN pin 1 should be an output, right? We're just setting these all up as outputs. And then the loop function uses this function called rotate, which I wrote, that I'll show you in just a second here. I'm going to say rotate 0, wait 1,000 milliseconds using our delay function, then rotate 1 and wait 1,000 milliseconds. So we sort of get some sense from having seen this motor fly around that rotate 0 is rotating in one direction and rotate 1 is rotating in the other direction. So I'll show you the rotate function that I wrote. I said if direction is 0, we rotate clockwise. For any other value, we'll rotate counterclockwise. That's just a choice I made. I could have said negative is one way, positive is the other, and 0 is not moving, right? But I chose to define this function as in this way. I'm going to first turn everything off, turn all off, another function that I wrote that I'll show you in a second. Here's the meat of the function, right? If direction equals 0, right, if dir equals 0, this value we pass in is 0, then I'm going to turn on PNP pin in position 0 and NPN pin in position 0. So in our case, that's going to be pins 0 and 10. And I said turn on, not turn high, because remember, like we talked about, and this is why it's good to remember how PNPs work. To get a PNP transistor to turn on, I need current to be flowing into my digital pin. So I need that digital pin to be low. I need to be at 0 volts to get this PNP transistor to turn on. To turn my NPN transistor to turn on, I need current flowing out of the base, right? Where's my example? I need current flowing from my pin into my NPN. So to turn my NPN transistor on, I need this digital pin to be at 5 volts, right? So important to remember that in this situation, there is definitely a difference between being high and being on, in this case, the transistors, right? So I said if my direction variable is 0, turn on this PNP and this NPN. Otherwise, turn on the other PNP and the other NPN. And by doing the code in this way, I basically guaranteed for myself that, you know, whenever I call this rotate function, I'm never going to accidentally turn on the wrong set of transistors and cause a dead short, right? I want to be able to use this function so I prevent myself from screwing up. And then just to show you the code that I wrote to this turn all off function, just something that seemed useful for me to have, right? It's going to step through all of my pins, turn the PNPs off by making those pins high, turn the NPNs off by making them low, and then wait 20 milliseconds, right? So I just thought it might be useful to say, hey, I want to have a function that whenever in my code I just want everything to go to 0 and stop, I'm just going to write a function called turn all off, and I'll put that in there. That'll be a useful thing for me to have. I only ended up using it one point in this code, but it seemed like a nice thing to have. So there's no harm in writing it in that way. Yeah, that sort of makes sense. Let's take a quick look at questions. Palmer says, can you 3D print a turret or something similarly fun for motor shaft on future demos? Certainly could. As Kenneth knows, blue tape is traditional. I'm sure I do have things that attach to motor shafts here. 3D printed a cassette with blue filament? Sure, blue filament would be great. We could spend a whole nother series of these videos on 3D printing, which would be a lot of fun. But blue tape is nice because then if I decide I don't want it attached, I can rip it off. My wife was actually suggesting that I attach some cute Totoro stickers to it, which I like that idea a great deal, but I'd feel very bad about ripping the nice Totoro stickers off of this motor here. So blue tape for tonight, I think it shall be. Oh, right. So that's using an H-bridge to control motors. stepping back through our slides, H bridge, right? So hopefully that makes sense. If not, I encourage you to build this circuit and play around with it. Make sure you get your digital pins hooked up correctly, and make sure that you're not blowing anything up. But I encourage you to play with an H bridge. It's a really good way of getting an understanding of what your NPN and PNP transistors are doing. Cool? Awesome. So before we move on to FETs, and I know we're coming. I used to say at the beginning of these that I'm shooting for a tight 90 minutes. I don't think I said that today because it's proved to be a very ambitious goal. But I know we're coming up on that, so we'll charge ahead a little bit. How to choose a transistor, right? Your kit probably came with some basic transistors, but after seeing this, you might be wondering, are those transistors right for my application? How do I know what transistor is right for me? And there's lots of possible ways to judge that, but here's 3 important characteristics that you should think about. The maximum collector emitter voltage, the maximum collector current, and the total device dissipation, right? All 3 of these things you can find in the data sheet for a transistor, and they'll tell you if the application is right for you. So let's think about these 3 things. So collector emitter voltage. And these things are true, by the way, for NPN or PNP transistors. Either way, these 3 characteristics apply. So let's go back to a circuit here. Yeah, so let's go back to our lamp circuit here. So in this circuit, I knew I needed to apply 12 volts to turn on my 12-volt lamp. So I needed a transistor whose maximum collector emitter voltage was at least 12 volts. Because when the transistor is turned off, the collector is going to be sitting, right, there's going to be no conduction here. My collector is going to be basically sitting at 12 volts and my emitter will be at ground. So choose a maximum collector emitter voltage that's at least as high as your maximum working voltage and probably a generous amount of margin on top of that as well. Maximum collector current, often called I sub C maximum. So I wish I had this diagram later in the slides, but to go back to our example here, right, I knew I needed 300 or so milliamps to flow through this lamp when it turned on. So I'm going to look for a transistor that has a maximum collector current, right? A maximum current flowing through this connector here of at least 300 milliamps, right? That's a pretty straightforward thing. If I knew I needed an amp of current, I'd want to look for a transistor that had at least an amp of maximum collector current. I'll show you in a moment when we go through these 3 things, and then I'll pull up an actual data sheet and I'll show you how to find these things when you're looking at a data sheet. It's coming back through the slides. Our last one here, is total device dissipation is a characteristic you want to look at. And that device dissipation at this point, dissipation just means like how much heat is released when this thing is turned on. For our purposes, because we're turning the transistors basically we're turning them all the way on by closing a switch or opening them up and letting no current flow. What we're really interested in is how much heat is this transistor itself going to generate when it's in that current flowing state. And the way that we will figure that out is, you remember I said before that the transistor man, when he's going to close that switch and turn it all the way on, he's going to have about a 0.2 to 0.3 volt drop across that transistor, right? So let's go back to a circuit here. Didn't think to put a circuit diagram at this point in the slides. When this circuit is all the way on, I'm going to have about a 0.2 volts to 0.3 volts across this transistor. I'm going to lose 0.2 to 0.3 volts in this transistor itself. So to figure out how much heat it is generating, right? Well, we know our current for this circuit was about 300 milliamps. We know our voltage drop is about 0.2 to 0.3 volts, and we have an equation that tells us the power that we're using when we have a current and a voltage, right? So if I have 12 volts, if I have 0.2 volts in our circuit and I have 300 milliamps, then head math, I have what, 60 milliwatts of power being released in that transistor? So really not a lot. And for the particular transistor that I'm using tonight, I see that my total device dissipation at what's called T sub A, ambient temperature or room temperature, my total device dissipation should be less than 625 milliwatts. Gonna be totally fine. Yeah, so that will be totally easy. You can also see, so just so you don't get confused, so total device dissipation at T sub A, this ambient temperature, that room temperature, nothing else attached to it, I can release up to 625 milliwatts from this thing. You also sometimes see this thing down here, T sub C, that's the temperature of the case of the device, right? If I can keep the temperature of the case of this device at room temperature, I can put 1.5 watts out of this thing, right? So if I were to take a big slab of copper or aluminum or metal, or run this thing underwater or in a bath of mineral oil, I could guarantee that the actual device itself was not going to get above room temperature. I can put a bunch more power out of it before the internals of it melt. So T sub A is ambient temperature, means room temperature. T sub C is actually locking that device to being room temperature using some active cooling. So don't get those two things confused. Cool. So those are the sort of the three things I would look at when choosing a transistor: is collector emitter voltage, like what is my working voltage, collector current, what's the maximum current I can put through it, and how much heat can I get out of it. And the heat one is generally not going to be a huge issue for our case. Transistors tend to be their most efficient in terms of heat wastage when they are fully on or fully off. It's when you're in the intermediate range that things get a little bit hotter. But for our purposes, something to watch out for, but not to worry about too much. So start thinking of questions, but I think it would be good to, let's jump into an actual data sheet, spoilers, and see where we find those pieces of data. So let's take a transistor we haven't looked at. Or take the transistor we looked at tonight, the 2N2222. So I'm just going to Google on camera here, 2N2222 data sheet. Let's get this a little bigger. And I see I have here's the one I actually use, PN22222A. Click on that, and I have my data sheet here, PN222A, NPN transistor, good. And here's that chart I was just looking at. So I have my maximum ratings for my collector emitter voltage. I have my continuous collector current, should be no more than 600 milliamps. I have my total device dissipation, and so on and so on. And I encourage you to go and scroll through some transistor data sheets and just see what details you can pick out. There's a lot of information here that you don't necessarily need for our applications, but you do get some interesting things, like if you come down here to DC current gain, right? This is that ratio that the transistor man is using to multiply that small base current to figure out how much collector current he should be emitting. And you can see it varies over a pretty wide range, and actually has some dependence on how much current is flowing in the collector and in the base. It varies based on temperature as well. This is a good place to poke around and see where things are, what you can learn about transistors in this way. Here's a little thing that I think Kenneth mentioned in the chat earlier, is this thing called a gain bandwidth product, which tells you how fast, in some ways, your transistor can switch on and off. And in this case, your gain bandwidth product, where you sort of stop being able to switch, is at least 300 megahertz, right? At least 300 million times a second. So for our application, even when we're doing pulse width modulation and we're turning on and off 500 times a second, this transistor is going to be just fine. Cool? So that's just a little peek into a data sheet. And like I say, there's all kinds of things in here that I don't make use of very often when I'm dealing with a simple switching application like this, but maybe worth looking into. But really, these maximum ratings that you'll find usually on the first page, collector emitter voltage, collector current, total device dissipation, are going to be the ones that are most relevant to you. Questions? Questions over here? Yeah, let us see. Aside from cost, is there a downside to using an oversized transistor? Kenneth's got the answer. Thanks, Kenneth. Kenneth's a good person to have in the chat for some of these things. Yeah, bigger transistors tend to be slower, but slower on the order of like a few megahertz or many kilohertz, as opposed to lots of hertz, like megahertz or gigahertz. When you get up into really high, like fast switching applications, then yeah, the minimizing transistor size can be super critical, or creating circuits that can take your circuit that provides a little bit of power but can switch really, really fast, using a transistor to try and eke that up to being a little bit more power but can still switch fast, and using that to drive a bigger transistor that can switch even more power but really, really fast, and sort of working your way up from there. Other questions? I'll just watch this little guy spin around for a while before I move on to FETs. Advantage to using a transistor instead of relays. Yeah, so Brian asked, why would we use a transistor instead of a relay? And so relays, we haven't talked about tonight, but they are the epitome of the mechanical version of solving this problem we set out to solve, which is, they are literally switches. They are an electromechanical device that uses a little electromagnet to physically open and close two pieces of metal, or sometimes more than two pieces of metal, to cause electrons to be able to flow between them. And there's a few reasons. Brian guesses size and cost. Yeah, for sure. Transistors or relays can tend to be huge, or can tend to be relatively big compared to transistors. Switching speed is another, right? If you think about two pieces of metal having to flap open and close, we're really limited on how fast that's able to happen. Whereas a transistor, right, we can turn on and off hundreds or thousands or millions or billions of times a second. There are some things that you can do with relays more simply than you can do with transistors. For example, let's say it was important to me that I have a signal, say at one point, that I want to be able to allow or disallow from passing to a separate point. Think about like an old-fashioned telephone, where you would be speaking into your handset, causing electrical signals to flow down a wire, and depending on who I'm calling, I want those signals to either get to my friend's house or not. Putting a relay in between, right? I guarantee that if I put those two pieces of metal together, then that signal is just going to see a wire between me and my friend, and if I open it up, they're going to see nothing. That kind of sort of direct metal-to-metal signal passing is not something, at least, that a bipolar transistor is able to do. It is something that a FET can do, although we're not really going to get into that application too much tonight. Relays also, if you're talking about really, really high currents, using a high current relay, like, you know, we're talking in the hundreds of amps or more, a transistor that's that big is going to probably be a little bit cost prohibitive and heat prohibitive, in the sense that if you have a really big relay of just two pieces of metal that are just slapping together, you now essentially have one big wire, and you can pass a lot of current through a high current relay. You can run into problems there, though, with if you have, say, a high voltage situation. When you start putting two, high voltage plates, let's say on your high voltage power line system, moving those closer and closer together, you might get arcing across those two plates before they can actually close together. That can damage your metal. So in high voltage situations, relays have to either be specialized or they may not be the perfect thing to use. Kenneth also has covered a lot of this in chat as well. Kenneth, it's good to have you in the chat as always. Hard to do PWM with relays? Yeah, for sure. So even switching at 500 times a second is going to be pretty aggressive for switching for anything but a really tiny relay. If you think about a xylophone that you're playing that dings at middle C, right, 440 hertz, boop, let's say. When you think about that vibrating, you can't see that xylophone key vibrating or that piano string or guitar string vibrating at 440 hertz, and that's less than the frequency that we would have to get a relay to move its mechanical contacts back and forth to be able to do PWM with. So anytime you're doing high-speed switching, like PWM at the hundreds or thousands of times a second, transistor with no moving parts is definitely the way to go. Good questions. Good questions. Yeah, Kenneth, you can say as opposed to lots of hertz, you wouldn't want to use a relay with lots of hertz. You can quote me on that. Awesome. Let's move on to FETs. Not this kind of FETs. We're going to talk about field effect transistors. So this is where I have to apologize for my terminology. I often just call bipolar transistors and FETs. They're both kinds of transistor. The bipolar junction transistor has two junctions, right? We say we have NPN or PNP. So the places where they meet, we have a PN or an NP junction. We have bipolar junctions. In a field effect transistor, the transistor action, that they call it, the act of taking a small action and causing a large current to flow, is being modulated by an electric field. So we have this field effect transistor that's using an electric field to make this happen, and that'll make sense in a second here. In terms of the actual devices themselves, they look a lot like your bipolar transistors. Unplug this guy. Sorry, Palmer, if this has been humming in your ear the whole time. I don't think I got any out in advance, but here's my box of FETs. And you'll see they look a lot like bipolar transistors. They come in very similar packaging a lot of the time, from small devices to bigger devices. They get much bigger than this too, but I don't tend to use things that are enormous. And we'll see part of that is because FETs for some applications have better power handling. So using a small FET for high power isn't as much of a problem. Much like a bipolar transistor, all FETs have three terminals, and they have their own names. They have a drain, a gate, and a source. Much like our bipolar transistors had a collector, base, and emitter, FETs have a drain, a gate, and a source. Make sure, as always, that you know what pins on your FET are connected to which, so you don't cause unfortunate fires to happen. Check, and double check. This is a snip I took from the datasheet of this 2N7000 transistor. They did a really nice job, where I have pins 1, 2, 3. I see that 1 is the source, 2 is the gate, and 3 is the drain when looked at like this. So unlike bipolar transistors, for bipolar transistors, there were essentially two types. We came in all different sizes of them, but we had NPN and PNP, and that was all we had to worry about. For FETs, things do get a little more complicated, but don't worry, there's really only one family of them that's going to be useful for us for this application. I just want you to know these other types are out there, because when you're jumping around on the internet, mostly, and trying to find a solution to something, you're going to see people proposing all kinds of things and tossing around this terminology. I just don't want you to be scared by it. I want you to be able to get to the solution that you need, right? So, as opposed to having sort of one dimension of splitting our family of bipolar transistors up between NPN and PNP, there are sort of three axes that we can split up FETs on. We have MOSFETs and JFETs, which are metal oxide semiconductor field effect transistors and junction field effect transistors, which just refers to some of the details of how the actual inner construction of the FETs are done. One has a metal oxide semiconductor in the middle of its gate, has a little tiny piece of glass that's sitting in between two parts of the transistor as an insulator. The other has a silicon junction and doesn't have this piece of glass in it. So MOSFET versus JFET. They work a little different. We'll get there in a little bit. You have enhancement versus depletion mode, which I will get to in a little bit. And you have N-channel versus P-channel. It seems like a lot, and it seems like it could be a lot of complication. For today's purposes, we're going to focus on enhancement mode MOSFETs. And honestly, a lot of the time, that's what you're going to be using for 99% of the digital applications. You could have a depletion mode MOSFET, you could have a depletion mode JFET, but really, we're talking about enhancement mode MOSFETs. So we'll have N-channel and P-channel of these enhancement mode MOSFETs, which will function very much like NPN and PNP transistors, and honestly, that's why we're going to use them. I'll show you sort of when we get to the end why you might want to choose some of these other types, but if you're buying a MOSFET and you say, oh, it's an enhancement mode N-channel MOSFET, that's going to be fine for you. All the ones that are available on Adafruit and SparkFun, for example, are these enhancement mode MOSFETs, just to let you know. So, much like our NPN and PNP transistors, there are two flavors of MOSFET that we're going to make use of. We have this N-channel and this P-channel MOSFET. And not a coincidence that they're named similarly. They're using those same materials internally, this N-type material and this P-type material that have more or not enough electrons in them. And these are the symbols for the two of them. We have this N-channel MOSFET, which has our body diode, they call it unfortunately, pointing in, and this P-channel MOSFET pointing out. MOSFET symbols are kind of a mess, to be perfectly honest. There's lots of different variants of them. Some circuit illustrators will exclude this diode entirely. Some will put this gate symbol right in the middle here, so it's not entirely clear what type it is. You may have to do some sleuthing to be able to tell what kind of MOSFET the circuit designer intended for you to use. You might have to look up a data sheet to know what kind it is. For our purposes tonight, just to make things as clear as we can, this is going to be our symbol for N-channel MOSFET, and this will be our circuit for P-channel MOSFET. And I'll label them as we go along, so make sure as well. You might also see this symbol, this kind of MOSFET called an NMOS circuit, or a PMOS circuit for a P-channel MOSFET. That's just shorthand, right? We've got a metal oxide semiconductor N-channel, we'll call that an NMOS. We'll call this a PMOS. And we'll see that an NMOS, or an N-channel MOSFET, works a lot like an NPN transistor in function, and a P-channel MOSFET works a lot like a PNP transistor. Super duper handy. So here is the critical difference between bipolar transistors and field effect transistors. In our bipolar transistors, we remember a small current on that base caused a large current to be able to flow through our other two terminals. In a field effect transistor, a small voltage on the gate leads to a lot of current being able to flow between our other two terminals. In this case, our drain and our source. And in a lot of ways, that ability to allow more current to flow looks a lot like a shrinking resistance, a decreased resistance between our drain and our source. But no current flows through the gate of our FET, or to be perfectly honest, very, very, very little current. We're talking picoamps, thousandths of billionths of an amp, if I'm doing the sign. I'm not sure I've got that math right, but essentially, for our purposes, no current needs to flow. We only need to apply a voltage, and the FET will turn on. So we can think of a FET transistor man inside of our FET the same way we thought about a transistor man inside of our bipolar transistor, except that instead of watching an ammeter on the input side, he's looking at a voltmeter at the gate and decreasing or increasing the resistance between the drain and the source. Right? So same idea, right? He's looking at the voltmeter and he's saying, oh, as the voltage on my gate goes up, I should decrease the resistance between the other two terminals and allow more current to flow. So let's look at as the same example we did earlier, except this time we're going to build it with a FET. So you'll recall we have our 12 volt 4 watt light bulb. We want 333 milliamps to be able to flow. So we'll set up our FET circuit in the same way that we set up our transistor circuit earlier. We're going to use an N-channel FET. We're going to put it in the same place in the circuit that we put our NPN transistor. So we'll put a small voltage on the gate, and we'll connect our drain to our 12 volt light bulb, and we'll connect our source to ground. Note that we don't necessarily need a current limiting resistor here on the gate because, in theory, no current at all is going to flow, right? The whole point of putting that resistor there in our NPN transistor circuit is so that when we applied 5 volts from our Arduino, we wouldn't have unlimited current rushing through things. But the gate, in many ways, the symbol here for this FET is really indicative, right? It looks like there's a gap in the circuitry between the gate and the rest of the FET, and that's because, for many purposes, there is, right? There is no current that's going to jump that gap, or a very, very, very tiny current is going to jump that gap. In practice, it's not a bad idea to put a resistor between the Arduino and the MOSFET. There are some situations in which large transients, large sudden surges of current on the output side can couple back some current to the input side, and if you have a sensitive controller, it could be damaged. I've done lots of circuits where I connect the MOSFET gate directly to the Arduino. If you're being safe, putting a small resistor there, 100 ohms, 1,000 ohms, is not a bad idea. It does mean that your MOSFET will turn on or off somewhat slower because it will have to sort of overcome that resistance to get that gate up to voltage or down to 0 volts. But again, for our purposes, even a few thousand times a second is slow for most MOSFETs, so we're not super duper worried about it. So we are going to basically build this same circuit on our breadboard that we did before. And it's actually going to take me a second because I realize I think I'm going to have to cannibalize my other circuit to make this happen. And so you're going to get to watch me double check the data sheet to make sure I got this right. So I'm going to take my NPN transistor out. I'm going to put in, what am I going to put in? I think I have an IRLB transistor here that I wanted to make use of. Let's see. Well, I could do an IRF 510. That would be fine. We'll talk a little bit about choosing FETs as well, the same way we talked about choosing transistors. Let's see. I think I want to use a transistor I don't have on my bench. So here, you guys get to look at a waiting screen for a second while I grab it out of a box that's up here. Oh, this is that quality content that you folks tune in on Sunday nights for. There's nothing terribly exciting happening. You're not missing much. You just get a very unfortunate camera angle because of where this box is stored. Ah, that's better. So I am going to pull out, let's see. If I don't have the right transistor, then I will punt. Yes, I will punt. Let's make use of one of these. Let's use an IRF 510. That's a fairly decent general purpose transistor FET. Or we're going to watch a blank part of the benchmark. Yeah, also possible. So let me, this I think is our final demo of the night. You can get a little sense of how you might attack this problem. So I'm gonna pop my transistor out of its packaging here. The transistors and FETs that come in these sort of like with this metal tab packaging here come in these plastic tubes. These tubes, these transistor trays are meant to slot into a pick-and-place machine, which is the machine that automatically puts components into a circuit board in a manufacturing sense. When you're buying them in less than a full tube quantity, right? I went online and bought 5 of them. They just chopped down a bit of that tube and sold me the little bit that I needed, which means that the packaging holds this very snugly and is not entirely coming out when I need it to. There we go. So I'm going to make use of that particular FET. And like I say, I forgot to look up which pins are which on this transistor. So you get to watch me Google it live. So I'm going to do an IRF 510 data sheet. There we go. So let's see here. So I love this. When the data sheets have a 3D view like this, there's no way you can screw it up. So my gate pin is on the left, my drain is in the center, and my source is on the right. So let's come back to the table here. I've got my black pin is going to come in from my Arduino. It's going to attach through. I'm going to put this 220 ohm resistor that I used earlier in there between my Arduino and the gate. Like I say, not strictly speaking necessary, but not a bad idea. I'm going to connect my, where's my electron lamp? There we go. My 12-volt lamp as before. I'm going to connect to my drain, plug that in there, and then we'll need to get that wired up to power. I'm just going to plug that in directly. And then my source is going to connect to ground. I knew there was a demo I was forgetting, and it apparently was this one. So that'll be power and ground. I'll remember to turn on my power supply and everything. It's going to go so well, I'm sure. All right, so let's see. Turn the power supply off. We'll hook up our power rails on this side. There's 12 volts. There's our ground. We're going to hook this back up. I'm going to run that blink sketch again. We'll just turn this light bulb on and off with our transistor like we did earlier. We'll plug that into pin 13. And then much like before, I got to make sure that the ground pin of my Arduino is hooked up to the ground rail here. I want to share a common ground. All right, so that's plugged in. Ground, pin 13, great. Plug that back in. We're going to upload our blink sketch again. Let's make sure we got the right port and the right board. We'll upload that. And so we'll see we have our LED blinking away. And when I turn the power supply on, hopefully things don't blow up. And hopefully they work. We'll see if we have a loose connection. There we go. My wiring is a little bit loose. But there you can see. So I have my, much like we had my transistor turning on and off before, now I have my FET turning my transistor on and off as well. By applying a small voltage, in this case 5 volts to the gate, I'm turning that FET on and causing its resistance to decrease, and that's letting current flow through my light bulb. Oh, and my power supply, which is turned on, thank you, Kenneth, but it's set to 5 volts, so when be a little harder to hold this light bulb in place when I turn the voltage back up to 12 volts. There we go. But there we go. So much the same as we were using an NPN transistor to control current flowing through a load, now we're using an N-channel MOSFET in exactly the same way. One of the advantages, though, is that before, when we were driving our transistor with first 3 milliamps and then 20 milliamps, now we're driving that FET with 5 volts, but almost no current. So we could be driving a lot of these FETs in parallel or driving multiple from them off of a battery if we needed to, while drawing very, very little current. So that's driving a FET with an Arduino. Questions? While you think of them, I'm going to roll along. Thank you for bearing with me as we assembled that demo live. I realized I hadn't built it up beforehand. Sort of exciting. One thing I want to talk about just a little bit as we talk about thinking about how to use FETs is much like we determined that we needed to have a certain minimum amount of current to turn a transistor on to do what we wanted it to do. MOSFETs have this parameter called a threshold voltage, which is the minimum voltage you have to apply to the gate to get that FET to turn on. But remember that a threshold voltage doesn't mean that it's fully on, that it's as low resistance as it can be. That's just the voltage where it starts to turn on. So let's now, since I had this data sheet open for the FET that I used, this is the IRF 510. I just had some lying around from a previous product. Let's see what our threshold voltage is. Let's see, maximum ratings will come down here to specifications. I've got temperature, dynamic, total gate. Where's my, here we go. Gate source threshold voltage. Let's make that a little bigger so you can see it. So my minimum gate source threshold voltage is 2 volts and my maximum is 4 volts. So much like transistors, you remember that beta factor, that multiplying factor between base current and total current could vary pretty widely between transistors of the same type. For FETs, the threshold voltage is what varies wildly, right? So I know that the minimum voltage I would need to put across that gate to get it to start conducting is going to be at least 2 volts, but might for another transistor in this same package that we were monkeying about with, might be as high as 4 volts. There are ways for specific applications to get matched pairs, right, so that they have that same threshold voltage. But remember, so much like a transistor, where we said we wanted to sort of overdrive things to making sure we were getting the conduction, the amount of current that we needed, for a FET, you also want to be overdriving things with plenty of voltage to make sure that they are as turned on as you need them to be. In our case, we can see if we come up here, just getting a little bit ahead of ourselves, but since we had the data sheet open, as we were thinking about like what FET might we choose for a specific project, the maximum parameters for this particular FET, maximum drain source voltage, right? So the maximum voltage across that FET in this case is 100 volts, and I can put up to plus or minus 20 volts on that gate. So I know I want to apply at least 4 volts because that's going to be the minimum I need to start turning it on. 5 volts is going to be fine. If I had 10 volts available, that might not be a bad thing to apply. You want to kind of be overdriving your FETs to create the amount of conduction that you need and minimize heat losses in your MOSFET. Right, so threshold voltage doesn't mean fully on. Threshold voltage means start turning on. Let's see. If you're going to pick a transistor to do projects with, this is the one I was looking for a moment ago, and for some reason I just can't for the life of me find. This is a not bad one to choose. And it's one that's available on Adafruit and on SparkFun, the IRLB 8721. It's an N-channel enhancement mode MOSFET like I've been working with. It has a deliberately low threshold voltage of 1.3 to 2.1 volts, I want to say, which makes it attractive for driving things from an Arduino because you know it's going to start conducting at a very low voltage, and then it's going to, as you ramp that voltage up to 5 volts, the resistance across that FET is going to drop very rapidly. The L in IRLB here actually refers to it being a logic level FET. You can drive it with some digital logic like an Arduino. They're pretty cheap. They're kind of everywhere. So if you don't have any FETs to play with at the moment and you're looking for one to play with for driving loads or lamps or things like that, I would recommend something like like this one, the IRLB 8721. I put a couple of links in the description of this video for an assortment of transistors to play with and an assortment of FETs, and also an assortment of low current FETs. The 2N7000 we were looking at earlier is a decent low current FET. You can play with that as well. But to sort of give you an example of some parameters you might be looking at, right? This IRLB 8721 has a maximum voltage across it of only 30 volts as opposed to the one I'm playing with here that can handle 100 volts. But when you turn it on all of the way, when I put 10 volts at its gate, it's going to act like a resistor of 8.7 milliohms between its drain and its source, right? So we're basically going to be shorting its drain and its source together. So it makes it a really nice transistor for driving high current loads, right? Even if we put 10 amps through a transistor like this, remember that power equals voltage times current. So if I put 10 amps through a resistor that's turned all the way on, at 8.7 milliohms, it's going to be dissipating 10 times at 87 milliamps, almost no heat at all. That's a really good property to have. Let's take a quick break for questions, and then we'll push on a little bit here. Adafruit is closed temporarily. Yeah, DigiKey is also available. Mouser is a great place to find electronics components online these days. Got some on Amazon this week. Yeah, some MOSFETs and some LED strips. Yeah, things. Unfortunately, Adafruit, Adafruit.com is a great supplier for goods for sort of us hobbyists in the world and makers. When they boot back up, we should really do what we can to support them. They also distribute through Amazon and DigiKey, so if you want to support Adafruit in this time, you can order through their distributors. I'm going to skip those examples for now. And just to come to this circuit, because we haven't actually looked at the full circuit of driving a FET with an Arduino currently. So this is exactly the circuit that I've built up on the bench over here. I have my 12 volts, I have my 12 volt lamp, I have my lamp connected to the drain of our FET, the source is grounded, and the gate is connected to digital pin through a resistor. Like I say, you don't technically need this resistor. And in fact, as I was doing some research for today, their opinions are somewhat divided about whether if you're driving a FET with a microprocessor, should you put a resistor there? And the consensus seems to be if you're not doing anything at a tremendously high speed, and that's millions of times a second of switching for our purposes, a resistor there doesn't really hurt anything, and in some applications can help you, protect you from certain spurious things happening, if that makes sense. Yeah, here we go. Reduces ringing, voltage spikes, transient coupling back from the load to the gate, things like that. So I typically put a resistor there if I can. If I forget to, I'm not too stressed about it. So much like PNP transistors are the counterpart of NPN transistors, the counterpart of N-channel MOSFETs is a P-channel MOSFET. And as you can expect, it works just like a PNP transistor in terms of where you'd wire it into a circuit. And similarly, you need to turn a PNP transistor on. I should say, sorry, I'm gonna take a sip of my beer and we'll start that sentence over again. To turn a p-channel enhancement mode MOSFET on, the gate has to be at a lower voltage than the source in this case. So much like, remember we had to, when we turned our PNP transistor on, we had to turn this digital pin low to 0 volts. Same thing, right? Even though this is now a voltage controlled source, to turn this p-channel MOSFET on, I need to bring this gate low to 0 volts. But you can use them in circuits the same way you'd use a PNP transistor, right? I'm doing this high side switching to attach my p-channel transistor directly to my voltage and using that to drive my load. So most circuits that you can make with a PNP transistor, you can make with a p-channel MOSFET. You can make an H-bridge out of FETs, just like we did earlier with NPN and PNP transistors. I haven't bothered to build up one of those on the bench because, frankly, it would look exactly like the one we made earlier. But know that their uses in the circuit are essentially compatible, right? They're very similar in their functionality. NPN transistor, N-channel enhancement mode MOSFET, PNP transistor, P-channel enhancement mode MOSFET. Cool? So I think there were some questions earlier about why you would choose one versus the other for a given application. And there are a few reasons. These are the reasons that I consider important for a sort of our like level of making perspective. There are much broader uses, I will say, of both transistors and MOSFETs than we're encountering here today, which are, in the grand scheme of things, relatively low voltage, medium power consumption, relatively slow switching, right? If you're doing things like building a radio transmitter at very high voltage and very high frequency, or doing things like building an Ethernet transceiver, which has to be, you know, very small voltages but switching incredibly fast, I'm sure there are lots of other things to consider. But for our purposes, as you're thinking about one versus the other, these are the factors I would consider. Most FETs, and the logic level FETs kind of being an exception, to turn them on as much as you can, right, to get that resistance across them to be as low as possible, that gate voltage really wants to be close to about 10 volts. 5 volts will suffice for turning them on. I mean, certainly you can see we're running over here. This FET that I'm using, the IRF 510, you know, the resistance across it when it's on is not as low as it can be, but for my application, that's plenty fine. 300 milliamps all day long, not a problem, right? So this resistance across this FET right now might be in the hundreds of milliohms instead of the tens of milliohms. For this application, that's fine, but for some applications it might not be. So it's worth thinking about, do you need to be driving your FET as hard as you can be with, say, 10 or 15 volts, or is 5 volts from your Arduino sufficient? FETs, because they reduce their resistance so much when you get down to this, you know, these high drive levels on the gate, they tend to be more power efficient for driving large loads. So once we're talking in terms of, you know, hundreds of milliamps to amps to tens of amps, the kind of resistors, the kind of transistors that you're using, you can drive them to having such low resistances that they are going to have much less heat losses. Sorry, get this guy flashing again. There you go. Come on, baby. There you go. It's fine. Much less heat losses in a FET than in a transistor for most of those higher current applications. Transistors tend to have higher switching speeds, tend being a really loosey-goosey word. For our purposes, it doesn't really matter because, again, doing something hundreds or thousands of times a second is not really high speed in the sake of these devices. When you're looking at higher power levels, you can typically put several FETs in parallel, but putting transistors in parallel is not recommended. And what do I mean by parallel? Well, let's say I had an application where I needed to be passing dozens of amps through a single load, something that needed to get really remarkably hot, or a lamp that was passing thousands of watts of current, and I couldn't get a single transistor to do the job. It is relatively safe to take a second transistor, say a second IRF 510, plug its gate into the same place, its drain into the same power, and its source into ground, and put them right in the same parallel connection with your load. And most of the time, it will work just fine. They won't necessarily evenly share the load, right, because those threshold voltages might be different. But in terms of how they're going to behave when they start heating up, they will tend to, when they're absorbing that power that you're putting through them, as they heat, as an individual FET heats up, it will take less of the current through itself and sort of spread the load to the other FETs, which then themselves will heat up more and pass the current back to the first one. There's kind of this self-equalizing process that happens. That's not true of bipolar transistors. They don't tend to do that same kind of load sharing. So when you're thinking about really high current applications where you need to put multiple devices in parallel, FETs are preferred over BJTs for that kind of application, if that makes sense. I don't know that we necessarily need to go super down the rabbit hole into what the other kinds of FETs are. I had a good time making these slides for what they are, but I actually would encourage you to just download the slides and look through them later. The gist of it is they function very much like the FETs that we've already encountered, right? So we've been talking about enhancement mode FETs, which you have to apply a voltage to or take a voltage away from the source to turn on. Depletion mode FETs are actually doped in such a way that when you apply no voltage to the source, they are already on. So just to say it quickly, in case you encounter an example that needs one of these in the wild, this is the kind of FET we've been looking at, an enhancement mode FET, right? If I have an N-channel FET with 5 volts in the drain and 0 volts in the gate, it's off. I apply a little bit of voltage on the gate, it turns on. I apply more voltage and it turns more on, right? For a depletion mode FET, just for curiosity's sake, when you apply 0 volts on the gate, it is already significantly on, and to turn it off, you actually have to take the voltage negative, right? I turn it to negative 2.5 volts, it's just a little bit on, take it to say negative 5 volts, and it turns off. Some kind of niche applications where this is useful, oscillators being one, where it's having this property where when your gate is at 0 volts, it's on, and pulling it away from that turns it off. It's kind of a niche property. For most purposes, we're going to be using enhancement mode MOSFETs for most of our projects. Junction field effect, JFETs, junction field effect transistors, also a really niche product. There tend to be lower noise for oscillators. They're less susceptible to damage, but really what we should be looking at is enhancement mode MOSFETs. You sometimes see this, here's why I include these. If you Google online how to use FETs for Arduino, what you end up with is a lot of people focusing on covering all the parts of this FET family tree, JFETs and MOSFETs, depletion and enhancement. The parts you're really going to use for most of your projects are these enhancement mode MOSFETs over here that we've been talking about all night. I just want you to know that these other kinds exist, and some people devote equal column space to all of them. I don't think it's necessary. Cool. Questions before we move on to our 7-segment display examples? Let's see, why would you choose a logic level FET versus a BJT? The RGB LED strip tutorial I followed this week wanted me to use logic level MOSFETs. Could that have been done with BJTs? Is it because it had 3 FETs? Yeah, honestly, for the kind of like level of currents and powers that we're talking about, it generally makes no difference. Once you get up into like the 1, 2, 3, 5 amp range, I find that the FETs tend to be cheaper and more power efficient than the bipolar transistors at that power level. But in terms of the circuitry itself, no, there's not really much of a practical difference. Power level FETs just tend to be cheap these days, and they're easy to buy. So that's something that I tend to gravitate towards. Good question. So thank you for bearing with. That's the gist of transistors and FETs with Arduino. I know it was a lot of slides. Good. That's 76 slides into our evening. I know. Thank you for bearing with me. But I think knowing how to, if you take nothing else away from tonight, knowing how to use an NPN transistor to turn on and off a load, or use an N-channel FET, that will carry you through 90% of your projects. Because most of the time what you need to do is make sure that current flows or current doesn't flow, or we're going to put PWM on the control pin and make it dim that way. That will carry you through a lot of these things. So feel free, download the slides, take those circuit diagrams and use them. One of the things that we're going to use them for, these transistors and FETs we've been learning about all night, is continuing our 7-segment display example from last week. So you may recall that last week we looked at controlling one of these little 7-segment displays. Here, I've got one here, which have actually 8, contrary to the name, have these 8 individual LED display segments. We've got 1, 2, 3, 4, 5, 6, 7 that make up the number, and then this dot makes 8. And if you recall from last week, the way that these are wired, they can be wired one of 2 ways, where they are made of these 8 LEDs, and one side of them is connected to all together in common. In this example, the anodes are connected together. And then the cathodes, the downstream sides, are all individually broken out to a bunch of individual pins. So we apply some positive voltage, in our case, to one of our pins, and then we choose which of the other pins to ground to turn individual segments on to display some numbers. Cool? So that was how we drove a single-digit 7-segment display last week, and I sort of teased that we wouldn't be able to control multiple numbers without the help of transistors. And having spent the past 2 hours with me learning about transistors, we are now ready to drive multiple-digit 7-segment displays. And here's how we're going to do it. Just to give you an intuitive example, right? If I think about these two 7-segment displays here, what I have is two places, in my case, to inject a positive voltage, and then I choose which of their pins to ground in order to turn those segments on. So if I had enough control pins, I could control these two displays, at the same time. I could apply, in my case, 5 volts to the top side of them here, and then I would have, let's see, 8 plus 8, 16 different pins that I could selectively choose to ground, and that would individually turn on or off those individual segments. That's a perfectly reasonable way to do it, but it doesn't quite scale well, right? If I added a third display, now I need 24 pins, and if I added a fourth display, now I need 32 pins, I think. It's a math minor. Don't lean on me too much for that. So what we're really looking for is something that doesn't doesn't multiply our number of control pins every time we add a digit. Because what we'd like to do is control either like the 2-digit or the 4-digit displays that probably came in your getting started with Arduino kit if you're working from one. So what we are going to do is use some transistors to control them individually. So let me show you real quick the circuit that we're going to be using, and then we'll show you it on the table. This is the circuit we used last time, right? So in case it was, you were not here last week, we had a circuit where we put this 5 volts from our Arduino into our display here, and then through our current limiting resistors, we selectively grounded individual segments to individually basically turn on and off 8 individual LEDs that are inside these packages, and then it was up to us to tell it which LEDs to turn on and which LEDs to turn off for each individual number, right? So this is the circuit that we're going to be working from today. It may look a little bit different because to be honest, I've stolen it from a different place on the internet, but its functionality is very the same. You'll see we have these current limiting resistors, and they're associated to these, in this case, these 7 ports, although we'll connect the dot up, that form the cathodes of our display. So in our case, I don't think I have a slide that shows this, these A, B, C, D, E, F, G, and dot connections are actually connected to all of the A segments in every LED. So in our case, this A connection port here is going to be connected to the A segment on digit 1, and the A segment on digit 2, and the A segment on digit 3, and the A segment on digit 4. The dot connection is the negative supply, if you will, the cathode for this dot, and this dot, and this dot, and this dot. And actually, before I get too far ahead of myself, I realize there's a diagram I should put in here, which I think will make this clearer, and it's in the datasheet for the display that we're going to be using tonight, which is this guy that I thought was really clear, and I think I will just show you. This is an LTC 5623, if it matters to any of you. So more Googling on stream. We will show you, here we go. I just think this has a really good diagram that explains what's actually going on inside this display, and it is this guy. Let's get that even bigger. So this particular display has 12 points of connection. So with just 12 connections, we're going to be able to instead of using those 32 pins that we were afraid we were going to have to use to control this thing, we're going to be able to do it with just 12. Here's how it's wired internally. Each of those digits has its own anode connection, its own positive supply point. In our case, pins 6, 8, 9, 12. Your device may vary. And then, as I said before, each of the cathodes, each of the negative sides of each of the A segments, you can see here, A, are all connected together and are connected to pin 11. Each of the B segments, B, are all connected to pin 7 together, and so on down the line. So what we're going to do to display, so if we wanted to display the same number on each of these displays, we could provide power to each of these pins, 6, 8, 9, 12, and then selectively ground individual of these pins, right? If I wanted to display, say, the number 1111, I could give power to all of our digits, and then I could ground segments B and C, right? Because those make up the number 1, boop, boop. It'd be ground pins 7 and 4, and they would display successfully. But what I would like to do is display numbers that have 4 digits that are not the same. So what we're going to do is use transistors to selectively apply a positive voltage to only one of these pins, each one of these anode pins at a time, and then selectively choose the cathodes to ground just for the number that we're on. To go back to our circuit diagram, what we're going to do here is use these PNP transistors. See, I told you transistors would tie back into it. We're going to use these PNP transistors to selectively apply that positive voltage to a specific anode pin for digit 1, 2, 3, or 4, and then selectively ground the cathodes for that pin just for that digit. So if that's not quite making sense yet, let's jump in the code, and I think it will. So let's get our code out. This code, as always, is also on jeff.glass/electronicsbash. This is the 7-segment 4-digit example. And if you're jumping into this fresh without doing last week's 7-segment demo, this may be a little bit fast. The code is just an expansion of what we wrote last week. So if the first part of this seems a little bit Greek, bear with me and go back and watch the 7-segment demo at the end of last week's video. And we'll be getting to the part that drives the 4 digits individually in just a second here. So here's what we've got. I'm going to define, first of all, which of my Arduino pins are connected to which of the segments, these output pins on our display, right? So just to go back to our data sheet, I know that like my segment A, which is pin 11 on the display, for me is my Arduino pin 9, and so on. I didn't do this very neatly, so they're not in a particular order. I'm going to hold that information in an array for my use later. And then I'm also going to create an array of where the anodes of my 4 PNP transistors are in the order that I want my digits to appear. It's going to be handy for me later. So my anodes are going to be connected to pins 13, 12, 11, and 10 of my Arduino. So if we look at our circuit just briefly here, I have my 4 PNP transistors here. They are connected to pins 10, 11, 12, 13 through these current limiting resistors here. This should all be feeling fairly familiar from earlier in the night, right? I've got my control pin, my resistor going to the base of my transistor, and my PNP transistor here. And these 4 white wires then are going to feed 5 volts, going to feed my power into the positive supply lines on the digits of my 4-digit display here, only when I turn the current on to flow through the base of that transistor. I'm going to use that transistor as a switch to turn on those digits. And the reason I'm using a transistor is because each of these pins, right, is going to be responsible for providing all of the power for all 8 digits or all 8 segments of a single digit of the display. And that's going to be more power than I want to rely on the Arduino putting out, right? If I want each of these segments to be, running at 10 milliamps, say, then if I turn all of them on at once, that's 80 milliamps, and that's more than the Arduino can stand. So I'm going to use a transistor as a switch to selectively pass that power into the positive pins when I want them to, if that sort of makes sense. So the rest of this code, if you followed along with us last week, will look familiar. If you didn't follow us along last week, you can skip it along a little bit. This is basically the part of the code where we're telling our code which segments should be on for which digits of our display. So to go back to our standard data sheet here, let's see if we've got our little, I don't think we have a display of which segment is which, but here we go. So you might see, here's our A segment of the digit, here's our B, our C, our D, E, F, and G. So if I wanted to make the number 1, I turn on segments B and C. If I want to make the number 3, I have to turn on A, B, C, D, and G. That's basically what this code here is encoding for us. We did a discussion last week of how exactly that code works. And then I'm going to write a new array called this display data, where I'm just going to hold whatever number I want to write out to this display. Just an easy place to store that information so I know where to get it when I want it later. And I'm going to write down that I'm going to use 4 digits, because that'll be a useful thing for me to know later. And then one of the things I'm going to make this display do is just count up from 0. So I've got some variables related to the counting that we'll use in a second here, right? The setup function is not particularly interesting. I'm going to make all of my pins connected to my cathodes outputs. My anodes are also outputs. And I'm using these functions turn off anode and turn off cathodes to turn things on and off. We'll get to those in a little bit, but for now, this is actually one of the advantages of wrapping these things in functions, is that I hope you'll trust me when I say turn off anode number 1 or 2 or 3, that I've written some code somewhere else that turns that anode off. In my case, because it's a PNP transistor, that means the pin goes high. But part of the nice thing about encapsulating some things like this in a function is, I've written some code that says turn off anode. I believe it works. If you believe it works, then don't worry too much about the implementation for now. We'll let that stand in place for some code that we don't really need to understand until we want to dig down deeper into the code itself, right? So looked at that way, right, I'm setting up my pins to be outputs, I'm setting up my anodes to be outputs, I'm turning my anodes off, and I'm turning my cathodes off. I have this turn off all cathodes function, right? So a nice way of wrapping up some functions with some details that we don't need to concern ourselves with for right now, right? So if you stay with me this long, here's the meat of it. Here is how we are going to individually control the 4 digits of our 4-digit 7-segment display. We're going to do a for loop, which is going to go from 0 to 1 less than a number of digits, so 0 through 3. So we're going to move through each digit in turn. And for each of those digits, we're going to turn its anode on We're going to supply 5 volts to the top end, if you will, the positive end of one of those LEDs. Let's say we'll start with digit 1. So I'm going to put 5 volts on this point using a PNP transistor, right? So I've turned that on. Then I'm going to set the cathodes to be on that are necessary for that particular digit, right? So what I'm doing here is I'm using the set cathodes function, which we'll look at in a little bit, and that's going to set the cathodes for the particular display data, which was all of this, data that encoded which segment should be on, for the value that we're looking at. So let's say I want to set the cathodes for digit 0. So I'm going to do set cathodes. I'm going to look at my display data array, and that's going to start as 0. And that's going to reference the segments for the digit 0 and turn on just those segments, or ground just those cathodes, if you will. So we applied some power, we grounded some cathodes, so that digit is going to be on. We're going to wait a moment. We're going to delay a small amount of time. I'm going to call it digit time, which I set for 1 millisecond to start with here. And then we're going to turn everything off. Turn off that anode, turn off all cathodes, right? And that's the end of our loop. So we're going to do that for our first digit, turn its anode on, ground the cathodes we want, wait a millisecond, turn everything off. Turn on our second anode, set the cathodes for that digit. Wait a second, turn everything off. Turn our anode on again, turn our third digit, and so on. So we're going to be moving from digits 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And if we do that fast enough, then the human eye, and if we're lucky, the camera, won't be able to see that we're actually turning them on and off. It'll all start to blend together in the same way that when we did our pulse width modulation demo, things were turning on and off so fast that we couldn't see it with our dumb human eyes. And the same way, we're going to turn our individual digits on and off so fast that we can't actually tell that we're turning on and off. So let me upload this code, run it for you, and hopefully you'll believe me. So in this case, I'm going to plug my Arduino in, come back to the table here. I think it's already running. Let's see here. Let's upload that code. Probably a little bit hard to see. Ooh, trouble uploading to board. Why? Oh, needed to set my port. We'll upload that code, and we should start at 0, and we'll start counting upward. So what's happening here, right, is we're very slowly counting up, but we're very quickly incrementing through each of these digits, right? We're turning the positive supply onto digit 1 and grounding, say, those 6 LED cathodes there that are making the digit 0. And then we're turning on the positive supply to digit 2 and then grounding those 6 cathodes and so on. In fact, I think I can show this to you better. Right now, I have in my loop here, you'll see I have this digit time of 1 millisecond. If I make that digit time a lot longer, let's say quarter of a second, and I'm going to make it count slower too, so it's a little easier to see. Then when I come back over here, so this is what it's doing when I'm asking it to display those digits, right? It's individually stepping forward. It's turning on the power to this digit and grounding its cathodes, then applying 5 volts to this digit and grounding its cathodes, then applying power to this digit and grounding its cathodes, and so on and so on. This is doing it at a rate of, changing over every quarter of a second. If I have this change over fast enough, then we'll see all those things blur together, and you won't be able to see it. Let's see if we can figure out what that minimum blur time is. So if I change the rate at which it increments to 100 milliseconds, no, we can still definitely see that. How about 10 milliseconds? Uploading. Pretty good, although on camera and certainly here in person, I can tell that they're flickering. We've sort of lost that like 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4 effect, but we can definitely still see that they're not solidly on. So let's go to 2 milliseconds and see if that's sufficient. Upload that. There we go. So now those things, I hope you'll believe me, will still flicker in there. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. But they're just doing it so quickly that my eye and the camera can't tell. Right? So this is the gist of what's called multiplexing, right? Where we're making use of the same pins to do multiple things. In this case, we're making use of the same set of cathode pins, this same set of grounding pins, but by selectively choosing which of the digits we're actually applying a positive voltage to, we're only seeing the LEDs in that digit light up at any given time. And by doing that fast enough, we can cause things to blur together so we can't see that it's happening. So that's the gist of driving a 4-digit, 7-segment display with an Arduino. Whew. And it only took us 2 weeks to get there. I think next week we're actually going to see a third way to do it. So this way, let's see, we said that driving a 4-digit 7-segment display sort of naively, right, with 4 positive pins and 32 ground pins, 36 pins? 36 pins we would have needed, right? A positive for each digit and 8 grounding pins for each digit. That's no good at all. This way, we've used 12 pins. We've got 4 of these positive pins and 8 of these grounding pins. So we've got 12 pins here. Next week, we will see a way to do it with only 6 pins. And it's going to make use of something called a shift register, which is going to basically take the action of these 8 grounding pins and wrap it all up into one device that's going to allow us to hand it some data, hand it 8 pieces of data to do something with, and it will ground those pins for us. But that's going to be a topic for next week, because that brings us to the end of today's topic. Before we close up, I do want to make sure and see if there's any further questions out there about using transistors, using FETs, using this 7-segment display here, or any of the code that we wrote for it. Well, I take what I think is my last sip of my Alley Time Pale Ale from Spiteful Brewery here in Chicago. Oh, which is just a very, very tasty refreshment on this night. Thanks, Becca. Yeah, I had a great time doing it. And really, like I say, like if you take nothing else away from tonight, like that critical circuit of like how you use an NPN transistor or an N-channel FET. Let's just go back to that circuit. Like there was just so many slides tonight, but I think if there was one that I wanted to leave you with, it would be this one. It would be this slide, right? A load, a FET, put a small voltage on it, it conducts current. This will get you through for a lot of the applications. And of course, the similar NPN transistor circuit that we looked at earlier tonight. Awesome, Michael. Thank you. Yeah, super. I hope it was helpful. And I encourage you to play around with NPN and PNP transistors. I know this was a ton. Like this was a lot of information to throw past. But I hope that it is at least straightforward enough to give you the confidence to start playing around with. You know, if your kit didn't come with transistors, I encourage you to buy a little kit of an assortment from Amazon or DigiKey or somewhere. There's a couple in the description that you can give a try to, and just play around. The worst that happens is you blow up something that cost you 10 cents. Things do sometimes blow up, but that's kind of the fun of it. I think it's you know, if having a little bit of that smoky smell in the air on your workbench tells you that you expanded your knowledge a little bit, and you can go back and figure out why something blew up. It's often, at least for me, because you got the wires mixed up, right? If you confuse some of your terminals and current was flowing where it shouldn't be, bad things can and will happen. But yeah, that is going to be our topic for tonight. So next week, here is what I think we should talk about. And I think every week that I've said, like, here's what we're going to talk about next week, it ended up morphing and changing just a little bit. But I think what we're going to do is, this is going to be our 6th week talking about Arduino and talking about code. And if you think back to our very first week, the very first thing we talked about was, what is an Arduino? And we established this metaphor that I keep leaning on, which is that an Arduino, or really any computer, is a device which takes some input, does some thinking, and produces some output, right? And all you're doing is choosing, what are my inputs, what is my thinking, and what are my outputs. In this case, my input is just time, right? I have no physical buttons or inputs or anything, but the device itself knows a little bit about how much time has passed. It does some thinking, right? The code that we wrote to know which segments mean what, where our things are connected, and it produces this output on our 4-digit 7-segment display that we prepared here. So that's what the input, thinking, output chain on this one looks like. And it seems to me that a lot of what we have done so far, and I'm not sad about it, is look at individual inputs and outputs and thinking, right? We've done, here is a servo, and here is how you control a servo. Here is a button, and here is how you read a button. Here is a knob, and here, but we haven't done a whole lot of hooking these things together. We've sort of looked at these individual tools, whether it's an output like a display or an LED or a transistor, or an input like a button or a switch or a potentiometer, or the thinking part. We've looked at some loops and arrays, but we've kind of looked at them in isolation. So I think what would be fun to do next week is dive slightly deeper into a programming project. We're still going to introduce a couple new outputs at least, and I think what we're going to play with next week is these multi-position LED displays. These are displays in my case of, I guess it's 8 by 10 and looks like 5 by 8 individual red LEDs that are all networked together. These probably came in your introduction to Arduino kit as well, or something like them. So these will be a fun thing to play with, and they're going to let us talk a little bit about those shift registers that I mentioned earlier. So there'll still be some hardware to talk about, but what I'd like to do is just take this hardware, and once you've introduced it, look at writing a very simple game for Arduino that's going to force us to think about not only inputs and outputs, but how we think about program logic and handling input in a timely fashion, producing output in a regular fashion, and how we can do all of these things simultaneously without our code getting in the way of itself. If you think way back to that first week, I said that the one trap that new programmers often fall into is blocking themselves into doing one thing at a time with an Arduino. You know, turn an LED on, then wait a second, then turn the LED off, then wait another second. And while you're waiting, you really can't do anything else. So we're going to look at some programming structures and some programming practices that allow us to make use of doing multiple things at once. And I think a fun way to do that will be to write a game for something like this. If you don't have these, honestly, they're easy and cheap to pick up, but also I think the programming practices that we will be making use of will be applicable to if you want to make your own game using, say, half a dozen LEDs or a buzzer or some other kind of output. I also intend for this code that we write together, right? A lot of the common ones that you get in the kit are 8 by 8 LEDs. I just don't happen to have one on hand. So we'll write some code that makes that game playable and defines the size of these play surfaces in, say, in a variable that allows us to change them very easily. And that's going to force us to write code in a way that doesn't directly depend on like magic numbers, right? That allows us to sort of change the parameters of our code and everything else should just work. I think that's going to be a really neat way for us to start digging into what it means to write a piece of code for the Arduino that's handling inputs and outputs and thinking in real time. So yeah, that's, I think, where we're going to go next week. As always, code will be going up on Jeff.glass over the course of the week, as well as slides, and we'll make a Facebook event for this as well, so people can get a reminder of when the thing is coming along. But yeah, I think that'll be neat. I think when you see that code go up, you will also see I will try and upload some incremental versions of that code, because I think a good chunk of our time next week is going to be, you know, write some base level code and then write some new features onto it and write some new features onto that and write some new features onto that. And so you'll see sort of an incremental process of that code going up. So hopefully, if you want to look at it ahead of time or follow along with, you can follow the thought process of how code gets built up to make a program and to make a little game that we can play at the end, and hopefully inspires you to write your own game on something like this display or something similar. But with that, I think we're going to call it a night here on this Sunday night. This is not the longest 90 minutes of a stream that we've ever had. We're right at 2:30 right now, which is pretty good for a 90-minute go. But for those of you who have stuck around for this entire time, thank you for spending another chill Sunday night with us. I hope it was worth it, and I hope you do some fun and powerful things with our transistors and FETs and play around. If you have questions, if you have comments, if you want to send me pictures, I would love to see pictures of what you're making. A couple of you already have, which is super cool. In fact, I want to show one off that I received just before we started tonight. This was a super cool video that someone sent me of doing the example we did last week of taking some serial control from a computer and putting up on a 7-segment display. I love getting stuff like this. This is super cool. So if you have stuff like this that you want to share, there's lots of ways you can do it. If you can put it in the comments of this video. Probably the easiest thing is find me on Twitter. I'm Jeffers on Twitter. Send me pictures, send me questions. Put them in Twitter or direct message me. I'm easy to find there. Put them in the comments of this video if you want to timestamp something. I don't know. I'm all over the place. Or send me an email. There's a contact form on jeff.glass that you could find me as well. But yeah, with that, thank you so much. Y'all are a bunch of great human beings. We'll be back here next week, same bat time, same bat channel, 7 p.m. Central, right here on YouTube. If you're not subscribed, if you want a reminder these things are happening, I know that's useful for me. You can hit the subscribe button down below. Not to be a YouTuber, but if you hit the subscribe button, you'll get a reminder when all these things are happening. We'll be right back here next week. Keep staying safe out there. Keep doing fun things. Keep washing your hands. I know I'm gonna go too. Chris says, don't forget to ring that bell. You can ring the bell or not. I don't really care. But yeah, it's nice to have a space where we come and tinker around and come and do these things. Send me your pictures, and I will see you next week. Thanks, y'all.